All right, welcome everybody to day 3 of the 2026 IEP workshop. As usual, the agenda is available electronically via the QR code at the registration desk. Also, the bingo game, get to know your workshop attendees, is also on a separate QR code. The bathrooms and water fountain are on the west side of the building underneath the stairs. Second floor bathrooms are in a similar location at the top of the stairs. Our poster room and overflow room are up the stairs in a hard left. If we need to evacuate the building in case of an emergency, follow emergency instructions, quietly and calmly find the nearest exit. Our gathering station is Franklin Roosevelt Park at 1615 9th Street. An emergency, assemble there and remain until instructed otherwise. The Wi-Fi is March 2026, and the M is lowercase. And as a reminder, there's no food or drink in the auditorium, sealed bottles only. We do need to keep this room clean, and so please consume in the lobby. Ted is drinking water over here during his plenary out of a coffee cup, so don't think that he's being hypocritical or anything. Just to keep his speaking voice up. If anyone needs an accommodation, such as the access to the elevator, the lactation room or hearing device, see Christine Job at the front desk or at the registration desk. This is a hybrid event, so we have an online audience. If you are joining us over the internet, please, if you have a question, fill it in the Q&A box, and if we get a chance, we'll ask the speakers. This workshop is being recorded. Assume anything you ask during the Q&A will also be recorded. There are 4 talks throughout the workshop that are not being recorded, so don't expect to be recorded for those talks. And they are noted in the program. There's no sitting on the back ledge of the auditorium. If you're in here, please either be seated in a seat or standing in the back. For those of you that have posters here, we ask that you take them down at lunch break today. So today we have our plenary speaker from 8:35 to 9:05. We have a second round of lightning talks from 9:07 to 9:47. A short break followed by the wetland habitat session from 10 to 11:40. Lunch will be 11:40 to 1:10. Then we have contaminants, nutrients, and water quality from 1:10 to 2:10. A short break followed by phytoplankton, algae, harmful algal blooms from 2:20 to 4. Another break, and then a couple of delta and longfin smelt talks, and then some closing remarks. And with that, get started. This one.
Our plenary speaker is Ted Flynn. With over 20 years of experience spanning both research and scientific management, Ted brings a deep, practical understanding of the complexities involved in environmental stewardship. As a public servant and scientist, Ted is intimately familiar with the rigorous standards required for regulatory science, as well as the friction that often comes with integrating new technologies into established routines. He also tells hilarious jokes and loves sending absurd Gen AI images to his unsuspecting friends and coworkers. Today, he's here to talk about the elephant in the room, generative AI. He will discuss how we can navigate the hype, the skepticism, and the very real concerns around this technology, and instead use it as a mindful, practical tool. Please welcome Ted to the Interagency Ecological Program Workshop stage, where he will present his talk, Change is Hard, Integrating Generative AI into Your Workflow Without Losing Your Mind or Your Soul.
So when Adam asked for a bio, I said, why don't we let the AI write it, and I'll let you guys guess which sentence I added. So anyway, thanks everybody for coming, and thanks to all the other plenary speakers and other folks who have discussed AI. They've covered a lot of ground that I won't have to, and hopefully we'll have plenty of time for questions at the end if folks have stuff they want to talk about. So yeah, so my talk is going to be much less about the nuts and certainly about the nuts and bolts of how AI works, and also less of a technical approach of looking at, you know, how you can use it for data science or numerical analyses. I'm going to look more for kind of the rest of us who might want to find ways to integrate this into our day-to-day workflow as scientists, but also as managers and other folks who all work in our interagency program. So, you know, why are we doing this talk? Why did we have this theme this year? I'm sure if any of you read the news, you don't have to look far to see that AI has dominated the conversation in a lot of ways over the last couple of years. And, you know, I think people are still trying to decide, is it just a novelty for making silly pictures? Is it, you know, the greatest thing ever? Is it going to totally change our lives and make everything better? And we're all going to have to work 1 hour a week and just spend the rest of the time doing whatever? Or is it a threat? Is this going to be a, you know, Skynet situation where it takes over the world and we're all, you know, doing, I don't know, working in the electron mines? I'm not exactly sure what we would be doing in those situations, but I know I've certainly had kind of these Google Maps moments, or these Napster moments, as I think of them, these with AI, where you sit down and you try something and it's so much better than anything you've seen. You know, with Google Maps, right? I grew up, you know, printing out direction, you know, first paper maps and then printing out the trying to remember the name of the web. Yeah, and MapQuest, and then you take a wrong turn and all of a sudden you're off the map and you don't know where you are and you're lost in the middle of the countryside. And then you see all of a sudden a thing on your phone that has a nice little blue dot that shows exactly where you are, anywhere you go, and thinking, oh my gosh, this is amazing. Nothing will be the same. So, and I also understand this kind of neo-Luddite impulse of, you know, we're scientists, we're used to change happening gradually over many, many years of dedicated hard work to make incremental changes. And sure, we have these paradigm shifts that happen now and again, but most of the work of the science that I do, and I think a lot of people in this room do, is dedicated to this long-term incremental improvements. And having something that's so disruptive, it's easy to have a reaction where you step back and you think, oh, I don't want any part of this. It's too scary, too new. And, you know, my opinion, I think throughout this talk, and again, this talk is a lot of my opinion, it's going to change how we work. There's no way around it. Our work lives are going to be very different 5 years from now, and maybe even sooner than that. But it won't change why what we do is important and why human scientists are essential to all of the things that we are addressing as a program, as you know, collaborators. So one of these, just to kind of show in case you've not really been paying attention, I wanted to show, this is a video, the Will Smith eating spaghetti has become kind of a meme for generative AI, certainly when it comes to video. This came out in 2023, so just a little, even less than 3 years ago. And it's kind of terrifying, right? And everybody laughed and like, oh, haha, look at these silly computers trying to do what we do. And then within less than 2 years, this is Google's version last year. So that's the, not even the latest. This is Google Veo from 2025. It's pretty good. And then this is from Seed Dance, which I think is from the company ByteDance. It came out in February of this year.
That's the good stuff. And that's a wrap.
So I'll point out that is all AI. Will Smith was not involved in that at all. That is all computers that created that video. My wife told me it was terrifying and she never wanted to watch it again, which I understand. But that's less than 3 years of change in the capability of these models. And if you are waiting back to see what these things can do for you and in your work, whether in your personal life or your workflow, it's worth checking out. But also at the same time, these headlines, these are all from the last few months, you know, people getting laid off. These have real impacts to people. People are losing their jobs, whether or not that's directly because of AI or because the people who are laying them off are using it as an excuse to cut staff. there's a lot of people who are really, really concerned about this impact on how we do our jobs and whether or not, you know, like Will Smith, who I'm sure is very concerned about being out of a job now. I think people are rightfully concerned about this. So, and now why me? I'm not an AI person. I don't write code. I am not a lawyer. I am not an information security or IT professional, but I'm pretty old. I've been around. I wrote school reports on a typewriter. I am also pretty nerdy. I love tech stuff. I love reading blogs about these new things. I love testing out new technology as it comes out. And I really like optimizing things. Folks who have worked in my group will know I'm always trying to think of like, well, what if we could find some new app or thing that would make this really boring task easier or faster? And I'm also pretty optimistic. I tend to think that things are generally not as bad as they seem, and that we will find a way to make this work in a positive way. And I think that about AI, but again, that's my opinion. So hopefully that's a helpful thing to contribute to the conversation. And ultimately, I believe science is a fundamentally human endeavor. Science is about explaining the natural world to each other. It's about us talking and having a conversation to understand how things that exist in the world, why they are, and not only that, but why they're important for us and for everyone who lives on Earth to understand, so that we can build a better planet that's safer, more sustainable, for a place for us all to live. And I think our scientific training makes us a perfect candidate to learn to use Gen AI, right? We are trained to be critically evaluating sources, right? I know for me, that was one of the fundamental things. Reading a paper, is this a good paper or a bad paper? Do they assert their hypotheses correctly? And do they have enough evidence to back their claims? That makes us effective at evaluating these Gen AI tools, which are going to give you answers that are demonstrably false or have at least misleading or all these things. And your training makes you good at doing that. And we are good at weighing the evidence to support decision-making and communicating with decision makers and providing them with the best available science to back their decisions. And Gen AI can help with that. Just like all computer tools, it can help us, it can harm us, but if used correctly, it's an incredibly valuable tool in our toolkit. We also know that scientific knowledge is just one of many ways of seeing the world, and it's because of this fundamental humanity of it, it's really something that can never be fully replicated by a computer. Technological change has also been fundamental to the progress of science, right? All of these things, whether it's the printing press, the microscope, even the high throughput DNA sequencer, a lot of the most fundamental breakthroughs in science have come on the back of technological change. And it provides incontrovertible evidence that certain things are true. And if we don't use these tools, even though this change can be very disruptive, we as public servants, whether or not you're an agency scientist or even if you work using public money, public grants at a university or at a consulting company, you are beholden to the public to use the best available tools at your disposal to create knowledge and to create evidence to back that decision making, to support public goals. And a lot of these things, when you look back at things that have become obsolete, would any of us want to go back to this? So the thing on the left, I remember talking to my PhD advisor's father, who was a professor as well, and he's like, that's what a spreadsheet is. That's what I learned about how a spreadsheet. And you had to sit there and you had to fill in each cell by hand because that's what was available. And you didn't have a calculator to do it. On the right is one of the original gas chromatographs. I don't know if anyone's worked in a chromatography lab, but I talked to another professor who was in his 90s when I was in grad school in the early 2000s, and he remembered the first gas chromatograph they got. And on the left there, that's not a screen, it's a roll of paper. And the way that they were able to integrate the curves on the gas chromatograph was by cutting the paper out with scissors and weighing it on a scale. And that, knowing the weight of paper, was able to tell them what is the area under the curve, because they didn't have computers that could do that for them, and it was easier to do it this way. I don't think any of us would want to go back to that. One of my favorite quotes is from the author Arthur C. Clarke, right? Any sufficiently advanced technology is indistinguishable from magic. And magic is scary because we don't know how it works. And I think that some of the talks earlier this week have really helped demystify what, it's not really artificial intelligence. It's really kind of just a very, very large statistical language model that kind of predicts what is the next right word in this situation to answer the question or the query that you've put in. It can seem like magic, and I know certainly some of the times I've done it. One of the first things I did when I first heard about some of these and the big changes they had, I put in some of the prompts that I had used as essay topics in high school, and it just spit out something that was 100 times better than anything I could have written at the age of 16, or probably even much later than that, and just realizing it took about 2 seconds. And that was kind of shocking that here's this thing that took me years and years to do, and here's a computer doing it in a way that looks exactly like a human would do it in, under a minute. That's kind of scary. And it seems like magic, but understanding both the mechanisms that we've gone over this week, I think can demystify that and allow you to use these things more mindfully. So if you are an expert, this is probably not the part of the talk for you. You probably know all about this. But if you're sitting on the sidelines and you're sitting on the fence saying, I'm not sure this is for me, I don't see how this would be useful, I would recommend start small. Start with a hobby. Maybe think of a new hobby that you're interested in. I know it's been very helpful for me picking up a new hobby, or even doing small tasks around the house. I was able to replace an electrical socket in my house by myself without electrocuting myself, through using these AI tools to make sure that, hey, this is all the safety things you do to make sure the electricity is off, and make sure you're grounded, and make sure you choose the right box and the right wiring and all these other things. It was incredibly helpful, and I did it and works just fine. So far, we'll see. And also keep in mind, when the product is free, you're the product. I heard this from my brother who worked at Google for many years. And a lot of the tech companies that are creating these tools, they're monetizing your data and your attention. And a lot of these will use that data and feed it back into the model. So be mindful when you're using these things. Don't share with them things you don't want shared with them, because they are going to become part of these large language models. And, I know this sometimes comes at a cost. And as some folks mentioned yesterday, a lot of these things do have a cost, right? In order to use the newest models, you do have to pay that. And I admit it, I do. I find it especially Google Gemini, I find it so useful in my day-to-day life that I do pay that subscription. I think it's worth it, just for myself personally. And also I'd recommend, look behind these kind of high level, right? Claude, Gemini, ChatGPT. There are some really specific tools, and I'm going to talk about one of them, Notebook LM here, that I find incredibly useful for scientific work and for personal work. Consensus and Elicit, I looked those up. I haven't had a chance to use them. They're more designed for scientific research specifically. Maybe give it a try. I haven't used them myself, but they look really interesting. So a lot of these tools are kind of, right, they're tools within tools. So Notebook LM is built within Google Gemini. It uses the capabilities of Google Gemini, but it's a self-contained thing. And there's also, so Gemini is, this vast thing of different capabilities. And one of them, which I use all the time, is called Nano Banana. And Nano Banana, it makes images. And I was talking with an IEP person during the week, and we were joking about salmon reds and how reds are spelled the same as Red Fox, the comedian from the 70s. And I don't know if any of you have ever watched Sanford and Son, but I thought it'd be pretty funny to think of salmon Red Fox and make a cartoon. And like I said, I just put in a prompt to Gemini and it made that. And now, I'm not passing it off as my own, but it was my idea. I don't know if anyone's ever made that joke before, and I'm certainly not capable of drawing an illustration anything near like that. But these things are not just text now. As you saw earlier, they're video, they're audio, they can make music, they can do all these other things. That doesn't mean that musicians are obsolete. It just means that, just like with the invention of recorded music, it doesn't mean it's not worthwhile to play an instrument. It is a fundamentally human thing, just like drawing or writing. And to use these tools effectively, you still know how to do that. It is still valuable to learn. So the one I wanted to highlight is this one, Notebook LM. So it was mentioned a bit yesterday. So the way that Notebook LM differs from, say, ChatGPT or these kind of frontline chatbots, which just have an open query and you just ask it questions, is that Notebook LM is self-contained. So if you see here on the anyway, anyway, the left column there, I created one for the recent Bay Delta Water Quality Control Plan. So I went in and I downloaded all of the old Bay Delta Water Quality Control Plans, all of the water right decisions, and a whole bunch of papers about all of those water right decisions. And then I had it build a model of all of that information. So this is all just PDFs that I found online and websites. And you can then query it. You can ask it questions. Say, how did the water quality regulations in the water rights decisions evolve since the 1970s? And it will answer it here in this central column. And the best part is, each one of its sentences is tied directly to the source. And if you click on that, it will tell you, I found this sentence in this document that explains exactly why I said what I said. And so you have that. It's not a black box anymore, right? You're telling it what to evaluate. And now that could be a limitation, because if you didn't put in something important, it won't know that. So it can skip things over. But it really, you know what you're querying. And one of the things that came up yesterday, right, is a question about AI slop, right? These just auto-generated junk that kind of muddy the waters, right? They're not real, they're not informed, but they're subsumed into these large language models. This is a way we can use our research skills as scientists to clear away that stuff, right? And because I think that this will be a rising issue, right? I know journal editors have faced this huge inundation of papers that were largely generated by Gen AI, right? That are wildly inaccurate and have, made up suppositions, fake references, all of this stuff. And as those things continue to get published and pulled into the scientific literature, it's going to become more and more important for us to be able to distinguish fact from fiction. And it can look very, very good, even though it's wrong. And so tools like this, I think, are tremendously valuable for, this is, I don't know if anyone's ever tried to read all these things. This is thousands of pages worth of documents. It's a huge effort. And also, my brain isn't that good anymore. I have a really hard time keeping track of a lot of this stuff. And then it also does silly things like it can make a podcast. So I asked it, Notebook LM, make a podcast about the change in water rights decisions in the Bay Delta Water Quality Control Plan. And this is what it did. If I can get it to.
All designed to pull that surplus water out of the estuary and ship it to the areas of need.
So put yourself in the shoes of the people managing this. If you have all these competing demands, cities that need drinking water, farms that need heavy irrigation to feed the country, and millions of migrating birds and native fish that just need a physical place to live, how do you even begin to decide who gets what without destroying the estuary in the process?
Well, it becomes an administrative nightmare very quickly. By the late 1970s, the pressure to share this water was so immense that the state realized their old way of doing things was completely broken.
How were they doing it before?
Historically, they had different agencies handling different problems.
So it's a 20-minute podcast. Be happy to share it with you if you want to listen to it. But it can do that for anything. You say you get a new table of contents from Limnology and Oceanography. You can download every single PDF, put it into Notebook LM, and ask it to make you a podcast and say, summarize all of the most recent papers. And you can listen to it on your way to work. Reading, I know I have a stack of to-read papers that is far longer than I'd like to admit, but I like podcasts and I have time when I'm grocery shopping or other things. This, things like this can be a way that you can keep up with the literature. And it doesn't mean you don't have to go and read it and look at the figures, but if you wanted to get a general idea, I think it's a pretty good way to start. And these all keep your data private. Google is very explicit with Notebook LM, at least, that none of the input or anything is shared with Gemini, so it stays on its own, which I like. And of course, there's a level of trust that you have to have with certain companies. And I think part of this, what I would recommend is really evaluating your own comfort level with these types of things. And it's incredibly valuable. So, we've talked a lot about the speed of bureaucracy, right? And how it's a real challenge for our agencies to keep up with the speed of this developments. And a lot of our current practices really focus on general guidelines, not a how-to of how to use these products, right? We know, okay, don't put personally identifiable information, right? Don't put proprietary or sensitive documents into something that's going to get pulled into an LLM that anyone on earth can see, right? Hiring managers out there, right? We don't put applications that people get. But at the same time, we can't rely on these official policies to guide how we're going to interface with this. Even if we don't use it ourselves, we are going to be given information that uses Gen AI, whether you're a hiring manager and you get applications that were created using Gen AI, whether you're hiring contractors, maybe the contractors are using it. We are going to have to know how to evaluate it one way or the other, even if we're not using it ourselves. And it's going to change expectations for productivity. Some of the hurdles or tools that we've used with the expectation that doing things like writing a statement of qualifications for a job is hard and takes time, that's not the case anymore. I challenge any of you to pick a job at random on CalCareers. Go in and then go to ChatGPT or whichever one you like, upload your resume, upload the 525 form, or this is for state people, sorry, upload the job description, upload that with your own resume and say, write me a 2-page statement of qualifications for this job based on my resume. Done. It's over. And it's not great. And I'm sure, hopefully most of us in the room would do a better job, but it's good enough. And it's gotten pretty hard to tell which ones are handwritten and which ones aren't anymore. And so those types of tools, they don't work anymore to keep the numbers of applications to a reasonable thing that we can all evaluate one at a time. And we're going to have, if we're interacting with any kind of external groups, we're going to have to know how to evaluate these products. It also will change how we report our data, because data will need to be AI accessible. Learning how to talk to these things is going to be incredibly important. So if you're thinking up a to-do list for learning to interact with Gen AI, I would challenge you, determine your own priorities and your own comfort level, and then learn to be a prompt engineer, right? Learn how talking and working with a Gen AI can seem very unsettling because it's so human-like, right? When you ask it a question, it responds like a human would. And like we talked about yesterday and the day before, right? These devices are specifically trained to be almost obsequiously nice to you. It is somewhat unsettling, but you don't talk to, that's not how you get an answer. For example, I build computers. When I'm troubleshooting it, I first started trying to figure out something is going wrong. I would say, something weird is happening to my motherboard and I don't know how to fix it. What's going on? And it would give me an answer, but it was very vague and unhelpful. So what I've actually started doing is keeping notes of the exact make model, right? I have a gigabyte DDR4 Z460X motherboard. And when I prompt it that way, it is incredibly helpful because it's able to go and find the manual and go do all that kind of boring scanning of PDFs from some tech company for me. And so learning how to ask a question that will give you a relevant answer is going to be very, very important to making useful products out of this. And also be transparent, be upfront when and how you use Gen AI. I know was talking to someone earlier this week who was saying that, submitting a paper to a journal and they're asking you to disclose how you use Gen AI. That's important so that folks know, yes, so I used Claude to help me write code in R to create the graphs and do the statistics. And, ultimately, I feel like our human expertise as scientists, managers, and technicians is still and will remain valuable, no matter how good Gen AI gets. We are still here putting our reputations on the line when we make decisions. We would make recommendations. That still comes from us. It doesn't matter if we used a calculator or R or something to do the math. That's still us making the assertion that if we change flows, I think this will happen, right? You are still putting yourself there. And no matter how good Gemini or Claude or ChatGPT gets, even with these agentic AIs, they're not going to be able to do that in a way that is authentic and valuable to decision makers. Try to think, what tasks can I accomplish now that are on my back burner that I couldn't get around to because I'm so busy doing this day-to-day busy work? I don't have this bandwidth to get this project done. If I can offload that busy work, can I do more? Can I pick up that side project? Will I have time for that? And just, I have faith that science is and will remain a human endeavor. And so I hope that's true. Maybe in a couple of years, you can watch this video and everyone will laugh at how naive I was. I hope not. But in any way, got some time for questions, so happy to answer. Thanks for your attention.
Yeah, we probably have time for 2 to 3 questions. Yeah, it's over there. Make sure you speak in the mic.
Hello. So you had mentioned a couple of uses using AI. These large language models are powered by large data centers that use a lot of electricity and a lot of water, oftentimes created in spaces with low income and communities that are affected by high electrical use, that are affecting their own dollars for their own electricity. Do you think using generative AI, whether there be images or within our workflow, is worth those ecological and human impacts?
I think that's a pretty complex question. And I mean, I don't really think again, this is all my opinion, right? It's just, I don't have the authority to make a general statement about that. But again, I think it's another, our modern lives are very complex, right? We don't get to choose when we come to work where the electricity that powers the building comes from. We don't get to choose how this building was designed, how energy, but we as taxpayers and as citizens get to vote for people who make decisions like, yeah, California state buildings should be LEED certified green buildings, right? They should be energy efficient, all of these things. And those are things that we get to decide. But it's another decision, and that's kind of what I say with your own comfort zone. You have to evaluate that for yourself, right? Just like some of us make decisions to live 20 miles away from our workspace and commute every day, whereas other ones live close so they can ride their bike or walk or take public transportation. You can decide to install energy efficient appliances at your house, or you can decide to have a wood-fired stove, right? These are all things that we all have to decide for ourselves, and that we have to decide as citizens how we want to vote for those decision makers and how they want to regulate that or not. And I think that's really the only way you can do it. That's not something I can really answer for any of us. So that's all really. And like I think, right, like look at all the boats we take out, those are all diesel engines, right? Is it worth, we've decided that it's worth burning that much diesel fuel every month out in the Delta to collect the data we collect. That's worth it to us. Someone else might not think so. Someone else might think it's a huge waste of resources. So it's those types of decisions are very, very complex. And I think when things are new and you remember how it used to be without using them, it's very easy to say, well, I'm just not going to do this. But I think you could probably make arguments that increased efficiency might outweigh those types of things. Or you might say, well, that just means we need additional regulations about where exactly these data centers are built, how they're built, and that. So that's my answer. I don't know if it's satisfactory, but.
No, it is. Not to take up another question, but I do have one I'd like to maybe hear. You mentioned that there are some papers that will ask, like, hey, how did you use some of this generative tools? If we're giving talks to like public, like schools or universities, things of that nature, with talking to the public, if someone is using generative AI in their workflow, even if they are disclosing that, do you think that would show like some distrust of like, how would you recommend keeping people to see this, like, oh, hey, these slides were created with AI. Maybe their conversation was also like, how do you navigate that? Because I feel like that's going to be a real concern. There are people like in schools that are being told, hey, you can't use AI, and their grades are being marked as 0 and F. So if we're, as scientists, showing them this using AI, but they're being told differently, that's a very contradictory conversation, especially if you're talking to people in sciences.
I don't really I feel like it's my place to say how educators want to do that. But certainly I would say my overall answer is just be transparent and be open about how and when it's appropriate. And these are new things. We're going to have to navigate that as a community, individually, between you and your supervisor, between you and your staff. You are going to have those conversations. Hey, it's okay to use Gen AI to make our code to generate, to make sure your statistics are correct, right? But if you're writing a report, don't just put a table and have it write the report for you, and then you don't read it and you copy it into Word and you say, hey, I wrote the report, right? Those are different things, but I think they're going to have to be decided on a case-by-case basis. I don't think we're going to have overarching, regulations for that. I think we're going to have to handle that ourselves, beyond maybe said very, very high level department level things.
Yeah, unfortunately, that took up all our time for questions. Sorry about that. Thank you, Ted. Awesome. Make sure you talk to Ted if you still have more questions. We are going to go ahead and move into the second session of lightning talks.
Morning. To start off, we have Meghan Holst from UC Davis Hammock Lab.
Hi, everyone. Thank you so much for being here. My name is Meghan Holst. I'm a postdoctoral fellow in Dr. Bruce Hammock's lab at University of California, Davis. And today I'm going to be presenting to you our results of a study looking at modeling contaminant detections and toxicity as a function of outflow in the Delta. We had two primary questions that were shaping our research. The first is, how do wet versus dry periods impact toxicity in the Delta? And the other being, is runoff or dilution a greater influence of detections and toxicity? On the one hand, we know that runoff is going to increase toxicity in the watershed, but on the other hand, increased flow will dilute toxicity. So at what point does what influencer take over is what we were trying to answer. We had two primary field sites that we used to investigate these questions. The first was Freeport at the Sacramento River, and the second was Vernalis on the San Joaquin River. And these are two of the major water influences into our watershed. So seeing big trends in chronic toxicity would have really big implications for downstream water quality, as well as ecosystem health implications. To answer these questions, we measured a couple of things. First, detections. So detections were when you go do a sampling event, any positive detection that you have during that sampling event divided by the total number of analytes that were tested for, and that standardized our detections as detections per unit effort. Then we wanted to study toxicity, and we measured that as something we're calling toxicity score, where we took the contaminant concentration and divided it by the EPA's benchmark for chronic toxicity. Now, obviously, that's going to be dependent based on taxa. So we looked at three groups: freshwater vertebrates, freshwater invertebrates, and non-vascular plants or phytoplankton. And then we measured detections and toxicity over time, water year type, and season. All of our data sources were publicly available, including from the United States Geological Survey, or USGS. They do the monitoring of contaminants in our watershed across the Delta, including at our two sites, Vernalis and Freeport, across decades. So we were able to pull quite a lot of data from them. The California Department of Water Resources has the day flow data where we're able to pull flow data specifically from our sites, again, Freeport and Vernalis. United States Environmental Protection Agency sets the benchmark data for taxa, and the California Data Exchange Center makes the water year type data. So we pulled data from all of those sources from 2000 to 2024, and we collated it into one large data set. And on top of looking at spatiotemporal trends, we wanted to look at what predictors were primarily influencing detections and toxicity. So for detections per unit effort, we created two models, one at each site. We did beta regression analysis for this model. And for toxicity score, we had 6 models, one at each site, and then again, one across each taxa. Our general model structure was our response variable as predicted by flow, precipitation, season, time since last rain in days, and then the interaction of flow and precipitation. When we look at overarching trends in the data, I'm going to orient you with some graphs here really quick. The left-hand side is our vertebrate taxa, the middle column is our invertebrates, and the right-hand column is our phytoplankton. The top row is our Freeport site, and the bottom row is our Vernalis site. When we take the annual mean over the entire study period, we see that toxicity score is declining over the last 2 decades, which was significant for vertebrates at both sites, invertebrates at Freeport and phytoplankton at Vernalis. When we look at the annual mean for detections across the study period, we see the same trend, where both at Freeport and Vernalis, they've significantly declined over the last 20 years. When we look at water year type, we see a really interesting relationship. The x-axis is a progression of water year type from critically dry years on the left-hand side to wet years on the right-hand side, and our response variable on the y-axis. Here I'm showing you both graphs for detections at both sites, but we had the same exact pattern across all response variables, all site and all taxa. And we see this really interesting bimodal relationship. It's really hard to understand what is causing this relationship, but a couple of thoughts that we had is we just saw the contaminants are decreasing over the study period. We also used to have wetter years in the past, and now we have drier years. So it's a potential that those things are influencing how we're seeing this pattern across wet and dry periods. What really is answering our questions is the response from our models. On the top row, you're going to see our response graphs from our detections models, and on the bottom row, you're going to see our response graphs from the toxicity score models. These are representative across all models, so the bottom row is across all site and all taxa. These are pretty representative of the patterns that we saw. When flow and precipitation interaction was not significant, we saw a slight negative effect of flow on detections and toxicity score. But we saw a pretty strong positive effect of precipitation on toxicity score and detections. Really interestingly, fall was significantly cleaner across years, where sometimes detections and toxicity score were 3 to 4 times better or less in fall compared to all other seasons. Now, the interaction between flow and precipitation really answers our dilution versus runoff question. When flow is really low and precipitation is really high, which is indicated with the different lines on the flow graph there, when precipitation is really high, it has a very large effect on detections and toxicity score. However, when flow is really high, we have a diminishing effect of precipitation, and flow is the larger indicator of detections and toxicity score. So, in summary, when flow is low, precipitation has a much higher impact on detections and toxicity. When flow is high, dilution starts to take over and has a larger effect than runoff. Fall is consistently the cleanest season that we have each year, and water has been getting cleaner over the last 2 decades, which is great news. And lastly, there isn't a linear relationship between wet and dry years with detections and toxicity score. With that, I'd like to thank UC Davis for hosting me as a postdoc and for state water contractors for funding this project. Thank you very much.
Have time for questions now. So we have time for a question or two. Yes.
I'm surprised that fall is so clean. Why is that so? I mean, flow is generally low and all that crap from the summer agricultural stuff is coming out. And could you explain that?
Yeah, that's a great question. I won't pretend that I'm an expert in contaminant and toxicity and chemical analytical chemistry data. I know that obviously agriculture is going to affect that when pesticides and things are applied, but I am not an expert in understanding the timing of those things, so I can't really speak to why fall is cleaner. What I'm showing here is just that the data from all of these data sources are showing that it's cleaner in fall. Yeah, thank you.
Any other questions? Quick one? Yes.
What do you feel about?
Oh, on the microphone. But,
yes.
Oh, you are on the microphone. I can't see it because the person's right.
How about now? So what do you feel about first flush? So the idea in the fall of, do you think you were able to capture that with the monitoring that was being done?
No, we did investigate first flush, but because USGS wasn't designating their sampling events around precipitation events, we couldn't actually examine that. Over the course of 20 years, there was only 6 days that were sampled directly after what we might consider as a first flush event, and it just wasn't enough to look at if there was trends with first flush. So we were also hoping that time since last rain would kind of get at that a little bit, but it didn't show up as a predictor for most of our models.
Great questions. Thanks so much, Megan. Next up, we have Lee Murai and Thomas Handley from DWR.
Thank you. Good morning. I'm Lee Murai. I'm an engineering geologist in the North Central Region office at DWR. And today I'm going to talk about our bathymetry work and also share some R&D that we think might be of use to ecologists and other scientists working in the Delta. At DWR's North Central Region office, we're responsible for mapping the underwater portions of the entire Delta. We monitor areas of erosion and deposition, provide bathymetry data for modeling, and support a variety of special studies. One example is at Georgiana Slough, where we have been supporting the bioacoustic fish fence, or BAF, also known as the fish disco, by monitoring riverbed changes around the structure. Another area of a project we support is the temporary barrier on Middle River, where we use our bathymetry data to assist with barrier removal and installation. So now I just want to talk about a little research and development we're working on, specifically submerged aquatic vegetation, or SAV mapping, and riverbed substrate mapping. So multi-beam bathymetry is a swath sonar system, and it sends and receives thousands of soundings per second. And the resulting data are high-resolution digital elevation models. And on the left here, you can see an example of a digital elevation model on San Joaquin River. And on the right is the actual soundings that are used to create the DEM. And this is hundreds of thousands of soundings. And on the edge of the channel here, you can see red high areas. And these are actually soundings of submerged aquatic vegetation. And here's a 2D slice through the point cloud. And you can see the SAV clearly sitting proud of the riverbed. And this is typically considered noise in our data, and so we remove it. And if I just click and back and forth, you can see our cleaning process and how we typically do it. However, we can take a different approach and first remove the noise and then retain and suppress the SAV soundings in our data set. And in this way, we can create two surfaces. We can create a clean bathymetric surface, as you can see in the blue here, and we can create another surface that retains the SAV in the data. If I click back and forth, you can see on the shoreline edge of the data set a little bit of difference. If you take these data into GIS and do a subtraction, you can actually calculate the SAV distribution on the riverbed. And you can also get metrics like height, volume, and density. And because we have good bathymetry in the same area, you can also do analyses like SAV by depth distribution or SAV by slope or other things like that. So like I said, multi-beam bathymetry is composed of many thousands of soundings per second. And for each one of those soundings, we also can record the reflected energy intensity off of the riverbed. And that's called backscatter. And that's really interesting because it gives you some information about the substrate in which you're sounding. And you can identify differences in substrate hardness and also substrate texture or roughness. And using this information, you can learn about the riverbed substrate and identify differences such as vegetation, and also distinguish different bottom types such as rock versus gravel, sand, mud, etc. I will say that ground truthing is necessary to go from an interpretation of the backscatter to an actual substrate type though. So here's Georgiana Slough again. This is the bathymetric surface. You can see the BAF in red. And this is what backscatter looks like. This is a backscatter mosaic. The high intensity returns are bright and the low intensity returns are dark. And here's an interpretation of the backscatter. And from this, you can see how much variability in bottom type actually exists that's not present just from bathymetry alone. And for example, you can see that bottom type in Georgiana Slough is actually different from the bottom type on the Sacramento River. Here's the Middle River barrier. You can see excavation marks in the middle area. And this is the backscatter of that same area. And again, high intensity is bright and low intensity is dark. And from here, we can see in more detail the influence of the barrier on sediment distribution in the area. And you can also see in the bright red center area, areas of riprap that were not removed during removal of the barrier. So what's the value of this information? Well, submerged aquatic vegetation mapping can allow us to better understand the prevalence and distribution of SAV in the Delta especially in areas where other methods of mapping SAB are not so successful. We can calculate metrics of vegetation such as height, density, et cetera. And it can be used as a tool for monitoring invasive vegetation species. Substrate mapping can provide insight into sedimentary processes in an area such as erosion and deposition, and can allow you to identify possible pathways for surface and groundwater interactions. And also habitat mapping for species that might have a specific association with a benthic substrate type. Lastly, I just want to mention that we have an NCRO bathymetry catalog that's in development, but this is a web map that allows you to interact with our data, cut profiles, and see data that exists in certain areas. This is the website. And these are our two groups, bathymetry and hydrography. And we also have a PLS surveyor in our group, Jacob Wright, who's not represented here. And with that, thank you for your time.
And again, we have time for a question or two. Oh, yeah, question.
Thank you. A question two. One is about repeat measures, and so the ability to see bathymetry changing over time. So what's your frequency of repeat? And then the second was, with some of that substrate mapping, can you look at density of clams or golden mussel or such?
Great questions, yeah. First, we're tasked with mapping the entire 700 miles of the Delta, and we're, right now, it looks like a 6-year cycle, so we basically repeat when needed, but if in areas of high dynamic change or special studies, we do more annual, like Georgiana Slough, we do annual surveys there. So it really depends on the area in the Delta. And then the second one is, I'm really interested in seeing if we can identify golden mussels. So we're starting to do that work because I've heard some evidence that there's golden mussels that are attaching to things on the riverbed. And so if that stuff is hard and it's in a matrix of soft sediments, that we may be able to resolve it from the backscatter.
Quick follow-up to that. If you found what you thought could be golden mussel, how would you then verify that it was golden mussel, not Potamicorbula?
Absolutely. So we have drop cameras, we have a submersible ROV that has video, and then sediment sampling. So this is R&D, so we're working on our methods, but definitely ground truthing and in situ observations are critical.
Thank you so much. Next up, we have Ravi Nagarajan from UC Davis. Come on.
Thank you. Thanks very much. And if you're feeling stressed or feeling down, or maybe you're contemplating AI and its role in your life, take a moment to visualize some positive things like the habitat restorations that are happening in the Delta. So there's about a dozen tidal wetland restorations happening in the Delta and Sassoon Marsh, shown in blue on the map. And monitoring is being performed at these restoration sites to understand their success and their efficacy by multiple groups, including the Fish Restoration Program and the UC Davis Sassoon Marsh Fish Study. And some of these monitoring paradigms include looking at paired reference sites shown in green on the map. So one of the main goals of these restoration programs is to benefit native fishes, like the Chinook salmon, including the listed winter and spring runs. And so as an eDNA scientist, geneticist, my question is, how can eDNA help in this setting and beyond for monitoring more generally in the Bay Delta? And so that's something we've been working on for a couple of years. And so in the context of restoration sites, we undertook a collaboration with FRP and the UC Davis Sassoon Marsh Fish Study to sample for eDNA in parallel with gear-based monitoring at a subset of restoration and reference sites over about a year period, multiple times. And so in this talk, I'll focus on Chinook eDNA, Chinook salmon eDNA as a case study, but I hope that the results could be extrapolated to other species as well. So basically, one of the main questions is how effective is multi-species versus single species monitoring? So we specifically wanted to compare qPCR, which detects a single species, to a multi-species method, metabarcoding. And so Lee Sanders, who did her master's thesis on this project, collected all the samples. She would collect samples at multiple sub-locations within a restoration or reference site and take multiple replicate samples there. And then in the lab, Grace Rosberg-Franco performed qPCR using a species-specific qPCR assay for Chinook salmon. And then on the same samples, Lee performed metabarcoding using 2 fish-specific genetic barcodes. And from that data, from the metabarcoding data, you get a whole suite of fish species, so an entire assemblage, I guess. And then for this talk, I'll be focusing on Chinook salmon, so pulling out the Chinook salmon eDNA signature, the relative read abundances from the metabarcoding data, and comparing that to the qPCR data. So here's just a particular example of results. So this was at the Tule Red restoration site, which is on the eastern edge of Grizzly Bay, sampled in December 2023. So in collaboration with FRP, we sampled at 3 sublocations, A, B, and C within the restoration site. And when we look at Grace's qPCR data, what we can see is that there's some spatial heterogeneity, and that sublocation A has quite a bit higher Chinook eDNA than the other subsites. So this is kind of a common trend where the eDNA is not just homogeneously spread out. It's patchily distributed, and there are hotspots that we can find. The other subsites or sub-sampling locations, B and C, there's also detectable eDNA at a much lower level for the most part. So there's this interesting kind of difference in the level of eDNA detection we find. So when we look at the corresponding Chinook metabarcoding data, we see a pretty similar pattern with high consistent detection of Chinook at location A and lower at B, with the exception of one sample that was kind of an oddball, only had data for one barcode for that. So generally, I think at the site level, methods are agreeing. If we look a little bit more broadly and kind of at a summary of our data, we can split our qPCR data into 3 categories. So no detection, and that's about 70% of samples. And then for the positive detections, we can split them into 2 bins. So that's qualitative detections that are at a low level, or higher level detections that can be quantified. So those lower level detections, they are real detections by our criteria with our QC standards and with negative controls controlled for, but they're at a much lower level and they can't be quantified into copies per liter like the quantitative higher detections. For the metabarcoding data, we get about 70% also of our samples are negative, and the positive samples show a distribution of relative abundances for Chinook that kind of form a long right tail. We look at our metabarcoding data a little bit more closely. Because we have 2 barcodes, we can compare them to each other and get some kind of internal confidence about the method. So when we look at the site level, we can see there's a really nice correlation between those 2 barcodes. So we can also use those qPCR categories, those 3 categories, to stratify our metabarcoding data. And when we do that, we see a nice agreement between the methods. When we take another approach to look at agreement, looking at the percent positive sites within a sample, we also see a nice agreement between the methods there as well. So overall, at the site level, we see that 83% of our sites are positive by one or both methods for Chinook eDNA. And there's some that are metabarcoding only, some that are qPCR only. We think that metabarcoding is competitive and can perform quite well on its own. So just kind of quickly to go through kind of a whirlwind summary of results. This is just the metabarcoding data across all the sites. And using the qPCR data as a guide, we can separate the positives into low and high. And when we do that, we can see that we're getting low and high detections of Chinook eDNA with metabarcoding at both restoration and reference sites. in multiple seasons from Suisun Marsh up to the Delta. And when we look at the matched qPCR catch data, there were 4 sampling events where we had where the monitoring crews captured Chinook salmon. Those 4 were all positive for eDNA, but 3 of the 4 were for low eDNA concentration. So that relationship still needs to be worked out a little bit. So we get a lot of data. So this is just the Chinook data. Obviously, we got a lot of other fish species detected, a lot of data per sampling effort. But understanding what it means, of course, is critical. And also we miss a lot of things with eDNA that we can't get. So for example, length or life stage or run type. But I just wanted to quickly give you a taste of maybe we can get some information about run type from eDNA. So Diana Munoz in the lab, who's right here, tested if she could detect the nuclear genotype for late migration in an eDNA sample. So she took samples that we had collected from the Nimbus hatchery in December of 2024 and used a Sherlock genetic approach, which differentiates between the late, which is fall and late fall, and the early winter run and spring run genotype. So to wrap it up, it worked great and she did a wonderful job. And so what we'd like to do is go forward with this and test this on those high eDNA samples from the previous slide. So thank you very much.
No time for questions, unfortunately. Next, we have Jonathan Huang from the Delta Stewardship Council.
Good morning, everyone. I'm Jonathan Huang. I'm a 2025 California Sea Grant State Fellow supporting the Delta Independent Science Board. And this is a presentation on a project to examine pesticide use in the Delta. So first, the Delta Independent Science Board is currently conducting a contaminant monitoring review with 3 goals in mind. The first goal is to assess the current monitoring programs for strength and areas of improvement and how these programs can inform decision-making regarding ecological risk. And second, to understand how monitoring is informed decision-making. And third, to review promising and emerging methods. This particular presentation that I'm doing is it is going to contribute to goal 1 of the review. But in 2025, a paper was published in Science by Boop et al. That concluded that exposure data required for risk assessment were not available for 1% of the chemicals with potential environmental concern in the US. In other words, at the national level, the existing monitoring data in the US is inadequate for conducting a risk assessment for most chemicals that are being used. And so the work I've done today is in part motivated by exploring how relevant this statement is, particularly for the Delta. And so we decided to focus on this effort on one chemical, which are pesticides, which are widely used across the Sacramento-San Joaquin watershed, as well as within the Delta. According to California's pesticide regulation, or Department of Pesticide Regulation, there are 1,031 registered active ingredients, and these can include pesticides that are used as herbicides, insecticides, fungicides, rodenticides, and more. And these pesticides have been applied for agricultural use, landscaping use, and then as well as for general pest control. Now, for monitoring the Delta, there are numerous pesticides that are currently being used, and they could potentially enter the waterways in multiple pathways. Some mentioned, alluded by previous presentation, where you can have runoff from stormwater or agricultural runoff through effluent or through direct application into the Delta or into the waterways. So we understand that given the current available resources, monitoring for all pesticides that are being used can be difficult. And so the first step is to create a prioritization process to identify the most important pesticides for aquatic health. And so this study is meant to provide information that can inform such a prioritization process. And so the first step of that process, we estimated a rough indicator to rank pesticides that should potentially be monitored. And this is an estimate of an indicator based off first how much pesticides are being applied, and second of how toxic the chemicals are to aquatic life. And we use a water quality criteria as a proxy for toxicity. From the amount applied, we use a database from California Department of Pesticide Regulation. They have a pesticide use report in which we identify the pesticides that are being applied in agriculture for agricultural use in the Delta and Sassoon Marsh. This database records the amount of pesticide use and the area is being applied on, and we're using the most recent publicly available data from DPR, and which is in 2023. And we selected for the 100 most prevalent pesticides based off the acreage applied across the Delta and Sassoon. For the water quality criteria, we selected a criteria that's most sensitive across aquatic organism groups. The criteria were taken from either literature-derived regulatory threshold levels, or RTLs, regional, national, or international databases, and we selected the criteria based off priority from that list that you see from the top to the bottom. And so for a little bit of the result, this is what we found out of the 100 chemicals that we looked at. We've overall found 98 of the 100. We found criteria for 98 of the 100 chemicals, 90 of which are from nationally derived sources. So majority are from US EPA's aquatic life benchmark. And we also found 8 from internationally, from international sources, and 2 that had no information at all, which we found. And so to show you some of the results, the initial results, I plotted the estimated potential risk against the prevalence, which is the application area within the Delta. Each of the points are color-coded so that it's classified by pesticide type, in which the red is fungicide, green is herbicide, blue is insecticide, and purple is other. The plot is so that if you move from bottom to top, you have increasing risk. If you move from left to right, you have increasing prevalence by area of area applied in the Delta. But to just highlight a few, I selected the top 15 highest risk pesticides, which are the names that you see on the graph. And among the top 15, you'll see that the application or the prevalence ranges widely. You have some that are widely applied, like the lambda cahilodrin all the way on the left, top left, but some like zeta cypermethrin all the way on the left side near the y-axis. The majority of the top 15 are classified as insecticides, but you also have some herbicides, with 5 of them being herbicides and 1 fungicide as well. And in fact, 5 of the pesticides of the highest potential risk are known as pyrethroids, in which 4 of the 5 are being considered in Central Valley Regional Water Quality Control Board's pyrethroid control plan. And so just to end, here are some takeaways, which is essentially just what I mentioned. Most pesticides of the highest potential risk to aquatic organisms were insecticides, but we also had some herbicides and fungicides within them. And then the 5 of the top ranked pesticides are in a group called pyrethroids, in which this was generally agreed upon by the findings of Bouma et al., which is the paper I just mentioned at the beginning. And it's just looking at the pesticide use and toxicity, doesn't include other factors such as environmental fate. And so the next step would to be consider those other factors to kind of derive a more appropriate risk assessment or estimate of potential risk. And also we're hoping to compare what we found with what is actually being monitored in the Delta. And so with that, I want to say thank you for listening. And if you have any questions, comments, feel free to contact this email.
Thank you very much. And finally, we have Huang from Contra Costa Water District. And if you have questions for any of the lightning talk speakers, there's a breakout.
Good morning, everyone. My name is Luhan. I'm the Associate Water Resource Specialist at Contra Costa Water District. I believe everyone in this room probably have heard about golden mussels and how awful they are. So today I want to pose like a special and crucial question here, like when do they spawn in the Delta? And some brief overview about this species. So they are native from southern China and Southeast Asia, and they have invaded the other part of Asia and South America. And since they were first detected in the Delta in October 2024, things has evolved like rapidly. So we know they have made their way like all the way south to LA County, and also some evidence say that they probably appear here like a little bit longer than we thought they are. And also they were introduced here by the ballast water, like everyone knows. And again, they have become like a huge problem for everyone living in the Delta. And this is a photo of what they look like. And these are mussels collected at our Middle River intake at Victoria Canal last September. And from this range of sizes, it tells us this is a well-established population already. And from the literatures in China and Brazil, we learned that temperature is the biological switch for golden mussel spawning. And they usually, the spawning usually begins when water temperature reaches like about 16 to 17 degrees C, and the peak activity starts when the temperature reaches 20 degrees C to 30 degrees C. That means like rapid reproduction. And also when temperature is even higher, they grow super, super fast. And it can reach up to 3.5 millimeter per month. And they are super cold tolerant. So even though in the winter and they can survive. And also we have a lovely environment here, which is great for them. So you can see from this temperature map, like the Delta's temperature almost never stays below 5 degrees C throughout the year. That means they can happily live here all year round. And about half the year, the water temperature exceeds 16 degrees C, means they are spawning. And a more detailed timeline is between like December to February, we have a colder water temperature and they usually just survive. But once the temperature crossed that threshold in March or April, they started the spawning. And from May to August to October is like the optimal season for their reproduction until November when like the spawning can finally take a break. And here comes a little mystery happened last year. This is the water temperature at Middle River at Victoria Canal. We can see the water temperature reach 16 degrees C in April. However, we didn't find any Voyager then. The first Voyager detection happened in June. So why is the 2-month delay? Does it mean there is like a secondary environmental factor that kind of also required for them to start the spawning, or like the current Voyager detection method just doesn't work for this like lower density and early cohort? I don't have the answer, but here's the good news. We have an upcoming research project that's gonna happen this year. And this is from a vast like partnership between CWD, East Bay Mud, Sacramento County, UC Berkeley, and UC Santa Barbara. And of course, the researchers at the UCs will do the work. And we already got funding from Water Research Foundation and Bureau of Reclamation. And the researchers, I won't say we here, but I mean the researchers, they will take a four-pronged approach. So we will we will collect adult mussels to check their gonad ripeness to see the spawning readiness. And we will also do validator sampling using plankton nettle and further verified by cross-polarized light microscopy and PCR to confirm the validator presence. Also, we will deploy different substrates to confirm. I didn't touch anything, I swear to God.
Sorry, folks, technical difficulties.
Sorry, folks, we're going to do the last few minutes without the screen display. You can do it.
Okay, so where will okay, we will deploy different substrates to check the recruitment. Also, it's a way to test which substrate material works the best. And we also will track temperature, EC, DO, calcium, and pH, just to see the environmental correlation here. What is the trigger? And actually, my last slide is the most important one because I have a very disturbing photo of the golden mussel encrusted artificial substrates from Port of Stockton. And I want to say that is the future we are looking at. We probably will see that across the Delta in a few years and maybe even in worse condition, and probably will show up in these results as well. And so the ultimate goal here is we need to move from this proactive management to a predictive and from reactive response to proactive management. And also we need more data and we need more research. And we need this funded project that we got for 2026 to last longer so we can have a longer time series. That is always good for science. And again, CWD loves science. And the most important thing is we invite collaboration and research. And if you have any ideas about a research question you have in mind to help us better understand this little creature, or you have some extra funding to spend, please contact me. I'm happy to connect people with the questions and with money. And yeah, that's my talk. And I have my email address on the last slide. My email address is lhan@ccwater.com.
Thank you. Sorry, Luhan. And thank you, everybody, for your patience. We're going to break until about 10 o'clock. Well, 10 o'clock, please be back in here. We'll work diligently to get the IT issues fixed. Thank you. All right, we'll go ahead and get started. Sorry again for the technical difficulties. If anybody really, I mean, for those of you that really wanted to see the last two slides, Luhan's email is in the abstract, the book of abstracts. So please look her up. And we're very sorry, Luhan and everybody. We also have a change in this next session. Anthony Donahue is unable to make it. So Kristen Dybala's speech or talk from 11:20. Excuse me, we're getting started. Thank you. You take this one, please.
Everyone, if you can please take your seats, we're going to be getting started.
Thank you. Thank you, Dan. As mentioned, we have a change to the agenda. Anthony Donahue is unable to make it, so Kristen Dybala will be moved up into that slot from 11 to 11:20, and then we'll add time to the lunch break. And we'll get started with wetland habitats. Dan?
Thank you, everyone. So at the start of our wetland habitat section, we've got some great talks. Like you said, we do have one lost talk, so we'll have extra break time. But to start us off, we've got Kimberly Evans, and I will let her introduce her slides. Thanks.
Hello, thank you so much. So my name is Kimberly Evans. I'm a graduate student at UC Davis in the Aquatic Research Collective in the Center for Watershed Sciences. And today I'm going to be taking you into Sassoon Marsh with an overview of the trends that we've been seeing in 2025. So yeah, let's jump into it. All right, the Sassoon Marsh fish study was initiated in 1979. It's this long-term data set that we have with consistent studying beginning in 1980. And it started with three main goals. The first, to track trends in sensitive species, native species, especially useful in the face of things like the pelagic organism decline. Second, to guide water management decisions, especially being situated downstream of things like the State Water Project. And third, to provide a baseline for research on wetlands, especially in the context of restorations. All right, so the system is unique in a lot of ways. I'm going to do kind of a broad general overview to start us off with this, with first going into the water and salinity structures that we have in place. So first we have the Sassoon Marsh salinity control gates. So those basically help keep the delta fresh, as well as keeping the Eastern Marsh fresh. There's also the Roaring River distribution system, which provides low salinity water to a bunch of lands in the Western Marsh. We have the wastewater treatment plant, which also releases tertiary treated wastewater into Sassoon Marsh up in Boynton Slough, which will be relevant when we're talking about salinity a little bit later on. And so these really complex structures in place make it a unique system. Not only that, we have the natural environment, so those bidirectional flows. It's a tidal system, but also is influenced by fresh water. So we have these things kind of at play that determine things like salinity, turbidity maximums, as well as species compositions and structure. Then lastly, most of Sassoon Marsh is made up of managed wetlands, and these are particularly managed for waterfowl. And so these like habitats create really interesting environments with higher residence time and all of these really unique systems that kind of help fish species as well. All right, so I'm going to kind of gloss over our methods. Don't worry, I won't talk about every single one of these things. But yeah, so in general, how do we sample such a complex system? So we have water quality that we look at. We do all of our standard measurements. And mid-2025, we also began taking extra measurements to couple it with a cool study that's happening and starting in June. And then we also have our trawl data. So we run otter trawls in 24 different sites across the Sassoon Marsh. We trawl for either 5 or 10 minutes, depending on the slough size. And that's really to get that mid-channel environment and kind of see what species are there. But to make sure it's comprehensive, we also do seines in a few sites to get more of that near-shore environment and make sure we're kind of getting that representative sample for the entire Sassoon Marsh. And speaking of how cool this data set is and how long-term it is, I'm going to plug my thesis project a little bit right now. So I'm using this data to look at split-tail abundances across the Sassoon Marsh from 1995 to 2024. And so I'm taking a bunch of those abiotic variables and using that to describe distributions within Sassoon, and then looking at a wetland index to be able to tell or be able to potentially predict abundances based off of their spawning habitat available. All right, so let's get into the variables and what we've actually been seeing in 2025. So we'll start off with salinity. So this year we had a fairly low salinity environment. Everything is relatively less salty in the first 8 months of the year. That's largely because we had a lot of delta outflow beginning of the year, in addition to the operation of the salinity control gates. So we see in September when the gate operation ceases, then we get this huge spike in salinity. In addition to that, I mentioned Boynton Slough a little bit earlier, which is where the tertiary water is fed into. You can see here that BY1, that site is the only one that didn't exhibit this huge spike in salinity going from August to September. So that's kind of a cool microhabitat that's available. Delta outflow. This is one of the main drivers for honestly everything in Sassoon Marsh. So we had this big spike in late winter with pretty average outflow up into December. Then dissolved oxygen, the averages are not super special. They pretty much follow exactly as we expect based off of historic averages. With, a bigger range in the beginning of the year. Those are kind of controlled by things like biotic processes, and colder water allows for higher thresholds. And then we see in the summer, as it gets a little bit warmer, those thresholds are changing a little bit. But all following within trends that we typically expect to see in Sassoon. This one is really interesting to me. So our water temperatures were a lot cooler this summer than we typically expect. And this is largely driven by, if you guys remember, we had a really cool summer this year. In the estuaries too, there's a lot of mixing. And so compared to systems like perhaps a lake, air temperature and water temperature are a little bit more tightly correlated to one another. So we had a really cool year compared to historic averages. Then lastly, it was a little bit more turbid than usual, with really high variability in Sassoon Marsh this year. And that's just a function of it being a really variable environment this year. We had this large flashy outflow, this interesting gradient of the environment. So as a result, we just see a very variable turbidity regime. Okay, now going into the fishes, which is my kind of favorite part of this talk. So interestingly enough, in our trawl trends, which is fairly consistent with the last few years, we had this pretty even split 50-50 between native and non-native species that we caught in our trawls. Unfortunately, none of those were smelt for a native species. So in our survey, this is our 10th year with no delta smelt. But fortunately, we did catch a few more longfin smelt this year than we have in the past, which is an interesting, an interesting finding. With split tail, also a fish that I really appreciate and love. A lot of the recruitment that we didn't really see in 2024 came back in 2025. And so we had a pretty nice burst of young age 0 fish that we were catching in Sassoon Marsh this year. But yeah, we really didn't see as much last year, which is kind of an interesting finding as well. Thinking about striped bass, so I didn't include this in this slide, but we had more striped bass in our trawls this year and less in our seines. But just looking at the breakdown for recruitment, we got this large spike after the spawning period, January through April. And then in those spring months, early summer months, we see the little babies coming out. And I remember being on the boat this day and picking through so many tiny little larval striped bass. With first mallard or spring branch being one of the most popular sites for us to catch striped bass. Then going into our shrimp and our prawns. So we have one non-native Siberian prawns and native California bay shrimp. We saw declines in both of these species. California bay shrimp do enjoy more salinity, full waters, whereas Siberian prawns can be a little bit fresher. So that could have been driving at least California bay shrimp abundances. I mean, we can see here in our monthly breakdown, it looks like there's declines, but this is just a store of their migration histories, where Siberian prawns, they're heading out and spawning in the summer months, whereas California bay shrimp spawn out in the bay in the early months and then come into Sassoon later on. And then our jellies and our mysids. So these are both fairly episodic species. Both of them are some of our invertebrate nectins that we look at. We saw a decline in our black sea jellyfish, an increase in our opossum shrimp or mysids, with a huge spike for black sea jellies when it got really salty in Sassoon Marsh, or when it started getting more salty in Sassoon Marsh. With, yeah, slowly trickle for catching less mysids later in the year. Then we have our clams. So these guys are, especially overbite clams, are really big ecosystem engineers in Sassoon Marsh. And this year we saw a little bit of an increase in both of them. With our overbite clams staying at low abundance for the past few years, likely also driven by it being a wet year again, consistent with other wet years that we've had for the past few years. With our Asian clam also increasing, and they like fresh water, which, yeah, makes sense. And then going into our seine trends. So unlike our trawl trends, we catch way, way more non-native species in our seines compared to our native species. And this is really driven by one main culprit, which is Mississippi silversides. So they, yeah, you guys might be familiar. So they had an increase in their abundance this year, with the ability for us to see some of the spikes where there's a lot more of those little babies fish popping in. Here's a breakdown of kind of those abundances by size, correlative to age class. So less than 30 millimeters, we consider those to be young of year. And they, yeah, had a giant spike when it was summertime. And then going into our Chinook salmon. So we caught a good amount in the beginning of the year. We really only see Chinook salmon in Sassoon Marsh from January to April. That's when the habitat is the best for them. So we caught a good amount this year, and then, yeah, and then later in those months, May through December, we don't typically catch many. But yeah, we saw increases in both of those, which is really great to see. Everybody loves salmon. And so, yeah, it seems like 2025 had good habitat for them. All right, and then I'm just going to summarize kind of everything I talked about. So overall, fairly even split between native and non-native species in the trawls. That wasn't the same case when we were looking at the seines. Non-natives, once again, were dominating those. We had a high magnitude peak of delta outflow, which was a little bit different than 2024, which had kind of two smaller peaks, but the timing was fairly similar. We had below average salinities up until we reached October, September area, cool summer water temperatures, and above average turbidity. And then something that I hadn't mentioned before is that we caught more species of fish in the trawls this year than we did in 2024, which was really interesting. And those species tend to be on either side of the spectrum, so way more salt tolerant or way more salinity-based fish, way more fresh fish. But in comparison, though, we didn't catch as many fish, and so that kind of seems like a trade-off for this year. And then in our seines, we caught one less species, so pretty comparable to 2024, but same trend, we caught a few less fish than we did last year. Sweet. And then with that, I would like to thank the Department of Water Resources, the Center for Watershed Sciences at UC Davis, the Aquatic Research Collective, and also the National Science Foundation. And here's my contact information. And yeah, I'm happy to take any questions.
We'll have time for 2, maybe 3 questions. So anyone have a question?
I was happy to see those catches of the juvenile salmon. Do you have any information on the ad clip frequency of those fish? Do they look like they were naturally produced?
Yeah, so we do typically see that they're unclipped fish, which is really interesting. Not necessarily to say that they're wild fish, but we typically see that they do have an adipose fin with pretty low frequency of clipped. What was that?
Do you mind waiting just for the mic?
How are Thule perch doing?
Yeah, let's see, in 2025, I'd have to review that to make sure, but I think they're doing pretty well, especially because they're kind of our hardy resident species. So I'd have to look at exact numbers to see how that changed from 2024 to 2025. But just thinking about like early this year in 26, we've caught a good amount. Yeah, we hit the gold mine one day, which was really awesome to see.
Move some over into Dutch slough.
Which slough?
Take some over into Dutch slough.
Oh, okay. I got you.
Hey, Kim, I know you're interested in split tail, and I was wondering what your thoughts are on just the variability in recruitment among years. It's so extreme between the very small and unexpectedly small recruitment from 2024 and then a relatively large recruitment this year. And I wonder what thoughts you have about that sort of variability.
Yeah, that variability was really interesting to me because in both years they were considered wet years, and in both years they also had access to spawning grounds. And so that low recruitment was kind of a head scratcher to me. So in general, there has to be kind of some other compounding factor, I think, that contributed to that low recruitment. But we had three really good water years. So perhaps it was, let's see, I believe 2022 was a pretty dry year. So it could have been kind of, left over from that. But in general, I would say that 2025 was pretty good because we had access to all those spawning grounds available from that high delta outflow that flooded a bunch of their habitat and allowed them to reproduce pretty well and show up. But yeah, the 2024 trend is interesting to me and something that I still have to dive a little bit into. Awesome, thank you.
Okay. Our next speaker is Elsie Platzer, a project I'm well familiar with, but I'm excited that she gets to share with you today.
Hi, everybody. Can you all hear me? Yes. Okay, this microphone I noticed is a little bit echoey, so I'm going to try and speak slower than usual and clearly because I like to rush. Hi, my name is Elsie, and I'm with the Center for Watershed Sciences, and I'm going to be here to talk to you today about a project we've done in collaboration with some folks from IEP, quantifying primary production exports from tidal wetlands in the San Francisco estuary. So, as you probably are already aware, the San Francisco estuary has a bit of a phytoplankton productivity problem. And as the landscape was transformed, lots of channelization occurred. Water was optimized to be conveyed very quickly into these very narrow and deep channels. So that reduced a lot of good habitat for phytoplankton. And then with the introduction of an invasive clam species that filter feeds phytoplankton like nobody's business, we saw a collapse in the population. And that led to some other knock-on ecological consequences, including the pelagic organism decline when 4 notable fish species saw their populations decline as well, especially delta smelt, which is now listed as critically endangered. So wetland restoration has been presented as a solution or a solution in part to these issues. And the driving theory behind wetland restoration for food web subsidy is that creating more wetlands that are shallow, that have a lot more light penetration into the water, that have more vegetation as opposed to those, rigid channels that we saw in a couple slides back. That would stimulate phytoplankton production, produce more food to feed the native fishes that we all love and care about so much. The one caveat to this theory is that we don't actually know how much phytoplankton is being created in these wetlands or if it's being exported to nearby waterways. So that was kind of the driving question behind the design of this study. So looking at this crude diagram of a tidal wetland, we can imagine that water coming from the tidal channel onto the wetland has some amount of net primary production during flood tide. And we hypothesize that water after sitting on the wetland and then later exiting during ebb tide will show an increase in that net primary production. So this is not only the hypothesis that we're going into this study with, it's kind of the hypothesis of food web focused restoration. So in order to test this, we collaborated with the California Department of Fish and Wildlife and worked closely with Dan, who's really the inventor of this study, and he can be seen on this slide filtering away diligently. He was responsible for coordinating nearly all of the field efforts, so thanks, Dan. And the field sampling scheme was extremely ambitious. A lot of work went into it. So looking at this idealized tide chart, these dark purple areas are kind of blocked off because they occur during the night, so you can't take a boat out during the night. It's not safe. Sampling was constrained to daylight hours, so you'll see that you had to pick days where there's a flood tide and an ebb tide that occurs during the day, and then during that flood period, we sampled 3 times at each site, so each arrow color represents a different site, and then again on the ebb 3 times at each site. And we had 2 pairs of sites in different areas of the estuary. So each day zipping back and forth between the paired sites. Day 1 was located in Sassoon Marsh, more of the brackish zone of the estuary. And those sites were Wings Landing, which is a restored wetland, as well as Rush Ranch, which is kind of an extant tidal remnant wetland. And then day 2, up in the North Delta, which is more fresh water, our paired sites were Lower Yolo Ranch and Yolo Flyway Farms. And this is the exhaustive and exhausting list of constituents that were collected at every single sampling event. So we looked at nutrients, including nitrite, nitrate, ammonia, phosphate. We collected organic matter, so kind of the schmutz in the water, the alive schmutz that's in the water, looking at DOC, DON, chlorophyll A, which is a good proxy for the density of phytoplankton in the water. Took note of environmental conditions, including temperature, turbidity, flow, that kind of thing. And then finally, we took water grabs for the oxygen depletion incubations, and that's how productivity rates were measured. So how we ran these incubations was we did a 12-hour light and dark cycle with our bottles. So basically, you take a bottle of water from the field, you split it into a light jar and a dark jar. You put the light jar under this grow light, and then you put the dark jar in a dark chamber, and you measure the change in dissolved oxygen in the water over 12 hours. So the light jar will give you a measure of net primary productivity, and the dark jar will give you a measure of how much respiration is going on. So now I'm going to get into some of our preliminary results, and I do want to emphasize preliminary results because we just got all of the data back last week, basically. So this is really the first crack at things. It is not, nobody jumped to any conclusions, okay? So the first piece that I want to pull out of these data is that we noticed that net primary production rates are often low or even negative regardless of tide, so in flood tide as well as ebb tide. And to us, that indicates that the system is dominated by heterotrophic processes a lot of the time. So if you'll take a look at this scatter plot, respiration is on the y-axis and net primary production. I said the opposite. Net primary production is on the x-axis and respiration is on the y-axis. And the colors are the sampling dates. So I want to draw your attention to this gray line at the 0 mark of net primary production. And you'll notice how many samples are located below the 0 line. Over half of our samples had negative net primary production going on. And when I say it has net negative primary production, what does that actually mean? So when we're looking at net primary production in these jars, it's a measure of the production or the photosynthesis in the jar. So obviously there's some phytoplankton in there that are photosynthesizing, but then also there's respiration going on. So the phytoplankton are photosynthesizing, but they're also breathing, so they're decreasing the oxygen that they just made. And then there's also some wetland microbes in there that are just breathing and not producing anything. They're kind of freeloaders. And when the net production is negative, that means respiration is the dominant process going on. So I've, in a really qualitative way, clustered the data into 3 different areas where I feel like different processes are going on. So if you'll look at this date cluster at the bottom, we have the blue day and the pink day, which I think are December and April. There's not a lot of respiration going on in those samples, but there's also not a lot of production. So I called this cluster just water because it's basically like if you just took a glass of water, maybe there's some microbes and some phytoplankton, but not a lot is going on. Then up here, we have what I called heterotrophy heaven. So you see that respiration is elevated, but production is low or negative. So it's dominated by heterotrophic processes. And then finally, this cluster over here, we finally have what we want to see, which is phytojuice, where respiration is medium to low, but we are seeing higher values of net production. But all of these samples are also only on one specific sampling day, which is very interesting, and I will come back to that briefly later on. So the second result I'm going to talk about is that production rates and magnitudes varied a lot by different factors, by tide, by season, by site. So what that means is that net primary production was not consistently boosted on ebb tide compared to flood tide after water spent time on a wetland. So on this graph, the x-axis is tide stage with the teal samples being flood tide, flood 1, 2, and 3. The orange samples are in ebb tide, ebb 1, 2, and 3. And net primary production is on the Y. And you can kind of see, looking at flood compared to ebb, that they look almost like mirror images of each other. And there's not a lot of difference as a whole between flood and ebb tides. And if you throw a quick pairwise test on that, it does confirm that observation. But then if you look at the data in a little more granular detail, you can start to pull out some more nuance. So these are net primary production measurements comparing flood and ebb tide per day at 2 of our sites. Wings Landing, which is a restoration site, Rush Ranch, which is that reference site in Sassoon Marsh. And you'll see that at Wings Landing on one of the days in September, ebb tide had much higher production. But then the trend flips the next month and flood tide outperforms ebb, and then the same occurs in the next month. So it's not that there's no difference at all between tides, it's that the trend isn't consistent, it's flipping back and forth. And then at Rush Ranch, at this reference site, there doesn't really seem to be a lot of difference between flood and ebb tide. So different dynamics are going on at different sites at different times. How confusing. And then finally, another thing that I want to point out is that chlorophyll, not tide, is a really strong predictor of net primary production. So that makes a lot of sense to us because chlorophyll describes how much phytoplankton is in the water. And if you have more phytoplankton, you're going to produce more. So this graph sets chlorophyll against net primary production. This should say R squared, but the R squared value is 0.75, which is really high for ecological trends because ecology is messy. But then you'll also notice that these samples up here are kind of driving the trend, and all of those samples are from the same day that we observed before, that really high production day, which also had a lot of chlorophyll in the water. So there's something really special about that day going on, but we don't know what it is yet. So kind of in conclusion, we had this hypothesis that net primary production on ebb tide would exceed primary production on flood. But what we're really finding is that net primary production is always variable. Sometimes it's higher in flood, sometimes it's higher in ebb, sometimes there's just not a lot of difference between the two. And we're going to have to do a lot more intensive investigating to find out why that is and to pull out some more detailed trends. So stay tuned. Thank you, and I'm happy to take questions.
There'll be definitely time for questions. We've got about 5 to 8 minutes.
I'm so glad there's time for questions. Thank you, Elsie. This is super great to see. I'm trying to get to one question. Sorry, I have like a lot in my head.
You could probably do 2 questions if you wanted to.
I don't want to be greedy. Not all tides are created equal, right? So have you looked at spring neap cycles or other aspects of tide beyond just stage over the last hour?
We will. I knew someone was going to ask this, and I did look at our special day and check the tides on that day, and it just wasn't anything special. So I don't think that is explaining at least our one day where we saw a lot of phytojuice in production, but that will be part of the analysis later on. I just haven't delved into it yet.
We'll take our next question from online.
It actually works well because Denise was mentioning that too. And she also asks, it seems like you have been seeing more productivity peaks during the autumnal equinox. Yes, no?
Yeah, thanks, Denise. That's a really interesting question. So during the fall, there's a lot more decomposition. So you can expect kind of a nutrient pulse in the estuary, but again, preliminary. I briefly looked at the nutrients and I didn't see a lot of stuff that was special around that time. We also sampled another day, maybe like 4 days before that special day. It was in a different area of the estuary and there wasn't as much production. So it's very localized and site dependent, and there's so many dynamics going on, so it's hard to say.
Hi.
Whoever has the mic and just started, go ahead.
So I have the mic back here. Okay, thanks. This is Levi in the corner. Great presentation. I love what you're doing. I love the experimental nature of it. Some of the questions have already touched on this, so I'm going to detail, but it seems like our hypotheses about what's happening in these restored tidal wetlands need to be really detailed with respect to cloud cover, solar radiation, tide inundation. There's a lot of different studies that have dealt with that. So I just thought, we can't just assume that our hypothesis is that it's always producing. The question is, when is it producing and how much is it producing? And I think thinking along those lines is going to be really helpful. And I know you're already going there, but I just think it's important to frame our hypotheses that way. The question I have, though, is also in addition to phytoplankton, which I know why we focus on that, especially in the Delta, there's a lot of other production going on. And I wonder if you can just talk about the other forms of production, benthic diatom mats that form all over the mudflat and over the vegetation, and the detrital pathways that are coming from all the vegetation. Those are also really important to consider for these types of habitats. Could you just comment on that?
Yes, thank you for that question. I will repeat it because you talk very fast. As a fellow fast talker, I see you. The question was, what about other forms of production, detrital pathways, emergent vegetation, all of those things? This study purposefully excluded those pathways because it was narrowly focused on assessing phytoplankton production. So those things are going on and they are important food sources, but they are not the focus of this study.
We have one clarifier.
Add a clarifier, Dan.
So one fun clarifier, and our next speaker will actually attest to this. We are going to try to get at some of the macrophyte community contributions, but the benthic portion, yes, that part we did. There wasn't much of a way to consider.
You have the mic. Go for it.
So thank you. Great to hear this update, Elsie. Well done. I'm wondering if you all have considered looking at precipitation in the preceding days and how that may be associated with perhaps a pulse of fresh water and a decrease in productivity during that ebb tide.
Yeah, that is a really good question. Precipitation, looking at precipitation in the days preceding sampling. Yes, we will look at that, just not yet.
Yeah, I had a question about the potential relationship between the dissolved organic matter, maybe DON, and respiration, because that might get at the detrital pathway. And in fact, the chlorophyll or the primary production you're measuring could actually be a food web subsidy, but what you're measuring in respiration is just the detrital dissolved fraction. And so I think it's maybe a little bit more nuanced than that. I'm curious whether a relationship would emerge between DOM and respiration rates.
Great question. Looking at relationship between DOM and respiration, I, again, briefly looked to see if there was a relationship and I didn't find anything interesting. I'm not going to rule it out yet because, again, really briefly looking at trends. And it's also hard to relate standing stocks to rates because thinking about, for example, with production, you can say, well, nutrients help production, but then if you only have a point measurement of nutrients at one time, you know, some of those have probably already been uptaken during the production process. So it kind of muddies the relationship. There's a time lag. It's not always easy to make that one-to-one connection. So I'll have to look further, but on first pass glance, I did not really see an increase in respiration in those samples that had higher DOM.
Got time for one or two more.
It was very interesting. I just wondered in terms of irradiance and light, and so whether you measured anything during the ebb and the flood, actually in situ, and then how that related to your grow lights as to what the difference, both in quantity and quality of light might be.
Yes, great question. We had many discussions about PAR in the early days of this study. We made a PAR map of the incubation tank because the lights are located at the middle and then the light kind of decreases as you go toward the edge. So we mapped out a band of where you can put the lights, where it's not too intense, but it's not too dark. And we did also take PAR measurements in the field. Looking at, again, our special day where there was a lot of production, it actually was quite turbid and the light penetration was quite low. So that's another interesting complication or caveat to those findings. But yes, we did look at PAR as well.
And that fits very well because most of those phytoplankton actually evolved where there's not much light. So often you find as soon as you have slightly high chlorophyll and usually about, 20 to 50% ambient light, you'll often get your Pmax.
Right, exactly. Do we have time for one more or are we getting hooked? Okay, I'm getting hooked. Bye.
Nice job. All right.
Still good.
Sorry.
That one.
Okay, here we go. Up next is Bailey Morrison. Thank you.
I want to make sure the pointer works for later. Okay. Hi, everyone. I'm Bailey Morrison. I'm a project scientist at UC Merced and was going to walk you guys through some of the work that we've been doing to map invasive aquatic vegetation throughout the whole delta using Sentinel-2 imagery.
And so quick run through that probably most people in this room are aware of, but like water in the Delta is very important to California. It's one of our main freshwater supplies for people, agriculture, industry. It fuels a $3 trillion economy and is home to over 600,000 people. But importantly for us is it's one of the big biodiversity hotspots in the world, but it also happens to be one of the most invaded ecosystems in the world. And they're very vulnerable to invasive species, to climate change. And at the same time, conservation and restoration is required by law in the state. Well, I need to make my slides a little bigger. So just to go through a couple technical terms, since I'll be using acronyms, invasive aquatic vegetation, you'll hear me say IAV, that's what we're talking about there. And this is a big major threat to global biodiversity. Within IAV, we have two other subcategories. There's submerged aquatic vegetation. So that's like Brazilian waterweed, coontail, kabomba, and you'll hear me say SAV. And then we have what we call floating aquatic vegetation, which includes species like water hyacinth, which is a true floater where they are up above the top of the water surface. Water primrose is technically more of an emergent species, but we include it in our classification for floating because of the creeping branches that go out over the water surface. And we're trying to have our emergent species like tule and cattail be mapped separately from water primrose, hyacinth, alligator weed, and those problematic invaders. So in terms of being a global threat to biodiversity, there's a lot of negative ecological impacts. So they alter environmental conditions, they can reduce native biodiversity, replace key habitats, and more recently there's some evidence that removing one invader like water hyacinth, which used to be the dominant one in the Delta, can actually open up space for another invader to come in like water primrose and blow up, so they can sometimes support each other. The map is showing from 2004 to 2019, the yellow is water primrose, how it's blown up over all those years up in the Liberty Island area. And then this is just a cool drone shot we did when we were out doing boat work over in Fern Island, which is in Wardcut. This was March, so in the summer, that all the water you see will be water primrose. So it's extensive, it covers tons of areas, it's problematic. But it's also challenging for management and restoration efforts and success. So they can decrease water quality, such as increasing sediment or impacting sediment transport, turbidity. They can affect water temperature, lower oxygen levels. And there's some newer evidence that SAV can help lead to algal blooms, the toxic algal blooms. And for more management specific challenges, you're getting blocked irrigation channels, navigation channels can be blocked, as well as impacting other water infrastructure. And then it can also impact flow management actions. And then it's also a threat to humans. So it increases agricultural costs a lot, especially when they get into these irrigation canals. We spend a boatload of money managing invasive species across the state, but just in terms of invasive aquatic vegetation, we've spent $60 million between 2013 and 2017, and the problem's only gotten worse. You can have increased flood risks and also increased disease risks from mosquito-borne diseases and whatnot. And so over time, there's now a recognized major data gap, which is a lack of a consistent long-term IAV monitoring program. This was determined by both the Delta Stewardship Council and the Independent Science Board. And currently there's also in decision-making frameworks, no one considers the effects management has on invasive aquatic vegetation. It's something that's on our radar, but how our choices and actions to manage everything in the Delta, we don't really know how that impacts either the spread or contraction of IAV. And so IEP highlighted that satellite remote sensing would be a useful solution to help build this monitoring program. And the State of the Bay Delta Science Report in 2023 specifically recommended establishing a consistent monitoring program, as well as developing tools for changing climates and also changing IAV communities. And so that's where our project's coming in to help fill this gap. So there's been a couple previous efforts in terms of using remote sensing to map invasive aquatic vegetation in the Delta. The first one, which I believe a number of people in here are aware of, is since 2004, almost every single summer or fall, we have what they call airborne imaging spectroscopy or hyperspectral airborne imagery flown over the Delta. And we get these really amazing, like 2 to 3 meter resolution, 1,000+ band imagery that Dr. Shriti Khanna and some others have worked on making some really amazing IAV class maps. I put the DOI in case people are interested in that. There's been a ton of studies using the airborne data related to like ecological dynamics, management efficacy studies, remote sensing methodology, phenological invasion mechanisms, like tons of stuff. And then because this has been so useful with the airborne, a former PhD student in our lab, Dr. Christiana Ade, was curious if we could do this with multispectral satellite or Earth orbiting remote sensing. And so she used Sentinel-2, which is from the European Space Agency, and found that she was able to create decent summer and fall models that with a few less classes than what the airborne could do, since we don't have as many spectral bands, but it's doable. And that was work that was also funded from the Delta Stewardship Council. So the goal of our overall project is to operationalize these remotely or satellite-based Sentinel-2 IAV class maps. That is our first major one, producing the maps, which I'll go into some of the differences between the airborne and Sentinel-2 in a second. But operationalizing isn't just having models that people can go grab, it's actually producing the maps and then handing over the infrastructure we come up with for our stakeholders, end users, and other people interested in the products, so that once we hand it over, these are continued to be able to be made as Sentinel keeps spitting out more and more images over time. Our second goal is to hit with what the State of the Bay Delta report also suggested, which is modeling tools to help assess how IAV will respond to past or future decision-making and management actions. And lastly, to ensure that the class maps are useful and beneficial for people, we're co-developing our mapping tools and products or performance metrics with members from the Delta Stewardship Council, the Department of Water Resources, California Department of Fish and Wildlife, and IEP, and collaborating with them closely to make sure that this is as useful as possible for everyone. So why are we interested in adding the satellite class maps to the airborne when we already have those? And so first thing, as I kind of mentioned already, the airborne imaging spectroscopy, which you'll see noted in future slides, is AIS. That's finer resolution at 2 to 3 meters, and we have over 1,000 spectral bands. So this one's really good at getting down at more species level. The Sentinel-2 imagery is, wouldn't call it the lowest spatial resolution. It's about 10 meters, which is still finer than Landsat, for example, and it's multispectral. So we have 12 spectral bands to use. But the reason we're interested in Sentinel is that it has a revisit about every 5 to 10 days over the Delta. And that's really important. Where the airborne, we only get, it's very expensive. We can only do this once a year, and it's dependent on funding. And I think everybody is very sore with the funding situation right now. It's guaranteed through 2027, but who knows if we'll be able to keep doing flights again. There was a break between 2009 to 2013 during the recession where these flights didn't occur. So we can fill in more temporally outside of summer and fall, which is great. It's free, which is also really great. So if we are not able to get funding, we'll at least still have some information, even if it's a little coarser. The one big difference is we can't control when the satellite flies over the Delta. So if it's very cloudy, you're not going to see below it, but luckily there's not too many, and we can't control the tides. So high tides tend to reduce our SAB class accuracy just because more of it's under the water. When we do the airborne flights, we can plan it so that we fly when it's low tide. And this graph just shows since 2016, when Sentinel-2 launched, how many images over the Delta had less than 25% cloud cover. So we're talking nearing 100 for many years, different images that we could produce a class map for. From Dr. Ade's dissertation work that she did identify some issues with her class model that needed to be improved to do this operationalization. First is a little bit of improved classification, which you'll see in a minute which classes we're using. There's also an issue with temporal transferability. So her model was really only, she had 3 separate models and they were only performing well for winter and or summer and fall. Her spring model had pretty poor performance and she couldn't even do a class on water hyacinth. And then we want some larger, fuller uncertainty assessments to go along with everything. And so I've been working on getting these class models improved. I was able to successfully make what I call like a multi-season classifier. So I don't need separate models. It's performing pretty well in spring, winter, fall, summer. And our accuracies are starting to near the airborne. They're a little less and I expect them to stay less. And again, we can't do species like down to the species level for every, like Phragmites we can't do, alligator weed we can't do. We can do water primrose and hyacinth. SAV is its own class. Even the airborne can't do separate SAV species. Then we've also improved the accuracies from Ade. So mine's the green on any of these. The airborne is done in purple and the dissertation work from Dr. Ade is in blue. And so the improvements have really stemmed from doing feature reduction in the model with the imagery that we've used. There's a lot of confusion between emergent and riparian plants. So we've created like a riparian mask using LiDAR data to help us identify heights, and anything that's too high is definitely not going to be Thule or cattail. There's some classes like hyacinth, which are becoming rarer and buried in places where you can't necessarily get with a boat. So we've developed some aerial photogrammetry techniques to try and fill in a little bit of pseudo-absence that we know is really good quality. And then part of the funding that we got from NASA has allowed us to start collecting in situ observations in spring and winter, because all the previous years have always been summer and fall. So all those things have helped. And so this is just a quick little GIF of going through 2024 for one date per month showing. So we have emergent, hyacinth, NPV is non-photosynthetic vegetation, so anything dead, water primrose, SAV, soil, water, and RIP is riparian vegetation. That's shrubs or trees. And so our second goal has been to do the modeling to assess IAV responses to management actions. We're using species distribution models. These are being created using a forward selection GLM model with Logit Link. We've broken it up into multiple habitats. So there's channel, flooded islands, and slow shallows, and it's being done on SAV, water hyacinth, and water primrose. And we're using a number of environmental variables from the 3D interim hydrodynamic model, which we're getting from Ed Gross at RMA. These are speed, salinity, and turbidity, and then we're using LiDAR-derived bathymetry for depth. There's going to be some additional years coming soon, but what I'm showing is for this 2015 model right now. And so for anyone who's done species distribution modeling, we picked these predictors specifically because they're part of the niche space for SAV, primrose, and water hyacinth, but specifically these are variables that can be impacted that we can measure by management actions. So a good example is the drought barrier can have impacts on salinity, turbidity, flow, and speed. And so we want to know, like, oh, when this barrier went up, what was the effect on these environmental variables, and how did that impact it cause IAV to spread, like submerge to increase or decrease or certain areas. So we're still trying to pick apart this type of information to help give some more science-based informed decision-making information. Doesn't mean that they'll decide not to do a barrier or something, but at least there's information going into the process of decision-making. And then really quickly, I just wanted to walk you through one of these heat maps to kind of show how we're understanding how these different variables impact SAV or FAV. And so species distribution models, they're just predicting the probability of occurrence given n-dimensional environmental combinations. And so what this is showing is where you have like a deep red color. So more depth, higher speeds. Where it's red, those conditions are not where, in this case, SAV can occur, and so we expect a 0% probability of seeing it, versus at more shallow depths and slower speeds where it's blue, we get a 100% chance, at least in terms of a fundamental niche, of SAV popping up. And to make it more complicated, I mentioned how it's n-dimensional. This is a way we're kind of trying to show a four-dimensional niche space. And so I'll walk you through it really quickly. This is why I wanted my pointer. Same idea where depth and speed are the X and Y axis. But if you start in this top left one, we have low salinity and low turbidity. So salinity running across, turbidity running from up to down. And what we can see in this first one is that for a fair amount of depths up until, I don't know, around -3, so 3 meters deep, water hyacinth can inhabit that condition. And in terms of speed, there's this sharp vertical line, which is suggesting that it doesn't matter really how fast it is within this range. Water hyacinth at up to about 3 meters depth has a 100% chance of occurring. And if you go down to high turbidity, so the 95th percent quantile in turbidity, this pattern doesn't change. So turbidity doesn't have effect, and that makes sense. Water hyacinth's a floater. So if their water has more sediment in it, they're not dependent on light under the water to survive because they're up above it. If we move to the high salinity, low turbidity case, we can see that this pattern does change, however. And so across a wide range of depths, or I guess you have a little bit of a wider amount of depths that it can go up to about 10 meters at this point, but there's a stark cutoff on speed. Can't explain exactly why. Dr. Shruti Khanna might have some answers. She's been working on these too. But again, if you go and move down to the high turbidity, high salinity condition, that pattern doesn't really shift, which is showing that turbidity in combination with high salinity isn't having an effect in terms of the conditions in which SAV thrives in. And so then going to the last part, or last goal for this project, is the co-development of our class mapper. So again, the maps are our main deliverable for this product, but we do want to make sure that this is as useful as possible and beneficial for anyone who's interested in the data. And so our major goal, and this is part of what I'm showing on the right, is what NASA calls their application readiness levels. So they help measure the impact and benefit and progress of the grant. And specifically what we need to do is demonstrate not only that there's a benefit or change in behavior based off the product that we're developing for our end users and stakeholders, but that it gets integrated into the organizations, or in our case, multiple organizations, operations, their decision-making frameworks. There needs to be sustained use. So after the project ends, it shouldn't just stop being used. And then we also need to make sure that we get our end users trained up so that they're able to maintain this after handover. It won't be, you see Merced, that will continue making sure this all works. Okay, I'm almost done. I have like a couple slides. So where we're at right now is we have a beta data set of these class maps available. They're on ArcGIS online. There's a direct download you can do. It's a stacked geotiff. There's a QR code that will take you right to this page. The stacked geotiff, you do not need a login or anything. You can just click it and it downloads, but this is the one that probably people who are good at GIS or coding would want to use. If you're newer, we have the map layers for 2024 as an individual layer that you do have to have an ArcGIS online account, but you can pop into ArcGIS Online's mapper, or it's also cloud-based, so it can open directly in their desktop app as well. This is likely while we're doing more testing and workshops and co-development, any new updates and changes are just going to go straight to this platform. So the newest versions will be the ones highlighted for people. And this isn't ArcGIS isn't necessarily where they're going to be stored, but it's really useful right now in terms of access for people and being able to play with it, especially since we have a lot of skill level range in terms of GIS. I'm working right now on having the full archive of Sentinel-2 imagery generated for these class maps. So from 2016 up until whatever the newest date is right now. There's a couple errors that we are aware of. One is the mask we're using doesn't include everybody's areas of interest. So if you are wanting to use this and your area is not in there, please email me. I can easily add in a shapefile and adjust the mask and make sure your area is in there. And two, SAV, since this is the first time that we're modeling it in winter and spring, when we have rainstorms, the turbidity goes up and it's having a mix up with SAV and water, so we're solving that. But otherwise, everything else is going really well. We're gonna be holding a workshop really soon in the end of April. I have to announce that when it's a little more planned out, but anyone who's interested, feel free to reach out, you can participate. And anyone who thinks this may be helpful for their decision-making, get in contact with us, please. So thank you to everybody. Thank you to our end users. Yeah, that's right. Let me just say thank you to a few people. Rosie Hartman from DWR, Dan and Shruti Khanna at CDFW and IEP, and Maggie Chrisman at DSC. You guys are awesome.
I really want to stress for you guys, the tools that they're producing are going to be really helpful for everybody. Moving into the future, you'll have access to veg imagery across the Delta monthly. So really great data set to look into.
If you want input on it, I recommend getting in contact.
Okay, unfortunately, we had one person drop out because they couldn't get here. But our final speaker is Kristen Dybala, and I'll let her take it from here.
All right. Thanks so much, Dan. Yeah, I'm Kristen Dybala. I'm an ecologist with Point Blue Conservation Science, and I'm here to share with you a bit about this project we're wrapping up in the next couple of months. Shifting gears a little bit to think about birds, but more broadly about tidal marsh and tidal wetland restoration in the Delta and in Sassoon. We've been thinking a lot about how we can contribute our data and expertise in understanding bird populations, but more broadly thinking about land management in the Delta and all of the many goals we have for the Delta ecosystem and concerns about trade-offs. Just to start with a little bit of background, we know tidal wetlands provide numerous ecosystem functions. SFEI illustrated a few of these really nicely in this graphic, including, of course, habitat for a number of species that we care about. And tidal wetland restoration is a key strategy in the Delta plan, with a lot of progress already made toward a restoration target. But of course, how well restoration projects perform in actually restoring the ecosystem functions we care about is going to depend on so many things. How we design and plan these restoration projects. And we can think about elevation and hydrology, location of the landscape, vegetation cover and composition, and on and on and on. Let's see. And so, careful monitoring of the effectiveness of these projects can tell us a lot about what designs are working for which ecosystem functions, and then feed into models and tools that could help us project the future benefits we might expect of different designs. And ultimately, I want to think about not just aiming for a restoration acreage target, but making sure that we're actually improving the health and resilience of the Delta ecosystem. So our goal with this project was to estimate at least some of the expected benefits of restoring tidal wetlands, but also to inform some decision-making, to help inform decision-making by examining things like how much of a difference it makes to fully meet the restoration target or not, whether more of those acres are in the Delta versus Sassoon Marsh, and then in terms of restoration design, whether it's a relatively simple levee breach versus a more engineered sediment moving elevation raising project that really maximizes tidal wetland vegetation. So to start, we looked to a recent effort led by the Delta Stewardship Council, for which they developed a few different conceptual restoration scenarios. This is an example of one of those. And I should emphasize that these scenarios were not meant to represent actual restoration plans, but more to illustrate a range of possibilities for where restoration could happen on the landscape. So we focused on 3 of these scenarios, and specifically the polygons included as potential tidal wetland restoration sites. And so here you're seeing all 3 scenarios layered on top of each other, and that's because they have a lot of polygons in common. But scenario 1 was a relatively modest scenario that represented primarily restoration work already underway or planned. And these are most of the polygons shown here and outlined in black. Scenarios 2 and 3 included everything in scenario 1 plus some extras. Both included a large area in Sassoon Marsh. Scenario 2 added an extra polygon in the Delta that's outlined in blue. And then scenario 3 added a couple more polygons in Sassoon Marsh outlined in red. So again, these are not restoration plans, but they are sort of representing variation in total acres restored and as well as whether there's more in the delta or Sassoon. And so then on top of these differences, we wanted to consider restoration method. And so thinking about elevations in these current, in these polygons, we found that many of these polygons contain areas that are already at subtidal elevations. And so we would expect some portions to become permanent open water. So this map represents a rough estimate of where that open water might be, and then where new tidal wetland vegetation might be. For comparison, we wanted to consider, that more engineered version of these designs that would kind of maximize tidal wetland vegetation. And so this is the map on the right represents that maximum vegetation scenario where you've altered elevations to some extent to allow as much tidal wetland veg as possible. So now we have 3 scenarios, each with an A and B design alternative. And we wanted to compare these scenarios to each other and to the current baseline landscape in terms of what impact each would have and how much benefit would be restored. And now, as I said earlier, of course, there are lots of benefits that could be estimated. Our strength is in understanding birds. We focused on bird habitat in tidal wetlands to start. The Delta and Sassoon provide habitat to an incredibly diverse bird community year-round. And they have, of course, been affected by the loss of all kinds of habitat, but especially wetland habitat and other changes to the landscape. So we expect, in general, that tidal wetland restoration should benefit some bird species. For this project, we selected 7 focal species that we expected to rely on tidal wetland habitat to some extent. And this includes 3 secretive marsh bird species. These are the ones on the top row, and then 4 songbird species on the bottom row. And many of these species have some special conservation status. So the California black rail is a state threatened species. Least bittern, common yellowthroat, song sparrow, and yellow-breasted chat are all California species of special concern. And then we have marsh wren and American bittern, and they don't have any particular, special conservation status, but they are really associated with wetland habitat and are good indicator species. At Point Blue, we have some long-term bird survey locations in the Delta and Sassoon. But as part of this project, we also conducted a more extensive set of point count surveys, strategically located to ensure we had a good representation of tidal wetlands across the landscape. And then we also deployed some autonomous recording units at a subset of those locations, left them out to collect audio throughout the day and night to help us pick up on some of those, especially some of those more secretive species. And then we also reached out to partners to fold in lots of other recent bird survey data. And so we incorporated some data from CDFW and USGS, as well as DWR and the UC Davis Museum of Wildlife and Fish Biology. The final data set included over 3,700 bird surveys collected since 2015 and over 4,200 hours of audio recorded by the ARUs, which we analyzed using BirdNet and then manually verified the presence of each of our species. We integrated all of these data together in a single analysis to fit species distribution models. And these models included, as predictors, land cover data from a recent land cover data set compiled by SFEI that included land cover classes and tidal status information. And you're seeing a version of this land cover data in the map. And then we also included some additional predictors like the tidal wetland patch size and the density of water channels surrounding each survey location. And I don't have time to get into the nitty-gritty of the modeling, but I'll just jump right to the results. So these are the model predicted distributions of suitable habitat for each of the focal species under the baseline, the current landscape. Our models overall fit well, and we're able to discriminate well between locations where these species were present and absent. And you can see right away some really big differences in the extent of suitable habitat across the 7 focal species. And certainly some of these are far more common than others. But across all of them, the vast majority of suitable habitat was really in the Central Delta and Sassoon Marsh. So these maps represented our baseline, and we generated similar maps for each of those restoration scenarios so that we could compare them to each other and estimate the net change from this baseline. And here I'm showing you just a summary overview of our results for secretive marsh bird species. So what you're looking at is essentially like a heat map. We've got our species in the rows, and then our A design alternatives on the left. Those are the ones with the more open water, less tidal wetland vegetation. And our B alternatives on the right with more tidal wetland vegetation. And then within each of those are 3 scenarios. And again, scenario 1 was relatively modest. Scenarios 2 and 3 had a lot more restoration. 2 had more in the delta, 3 had more in Sassoon. So I've color coded the effect sizes to show bigger increases in darker blue, and then statistically significant chart changes marked with a star. So we predicted increases in suitable habitat for black rail and American bittern across all of our scenarios and alternatives. But for black rail, much larger and more statistically significant increases under scenarios 2 and 3 with more acres restored, and especially under the B alternatives with more veg. For American bittern, there was relatively little difference across scenarios or alternatives. And I should say for black rail, scenarios 2 and B represented something like a 300% increase in suitable habitat from baseline. Unexpectedly, we estimated some possible small declines in suitable habitat for least bittern under scenarios 2 and 3, though not statistically significant. And then overall, thinking about secretive marsh birds as a group, we estimated the total suitable habitat for at least one of these species would increase and kind of follow the pattern for black rail. And then for comparison, for our songbird focal species, similar kind of setup here. We again find generally positive effects for most species. And here, scenarios 2 and 3 aren't much different from scenario 1, but again, we see much bigger increases for the B alternatives with more tidal wetland vegetation. Here again, we had one exception with yellow-breasted chat. This is another species like least bittern with relatively few detections in our data set. Under the B alternatives, all of the declines were statistically significant in this case. And for this species and for least bittern, I suspect this result may have to do with our assumption that some of the existing riparian vegetation would just get replaced by tidal wetland vegetation. And both of these species do have some association with kind of more shrubby areas. But again, overall here, we estimated increases in the total extent of suitable habitat for the songbirds as a group. Okay, so that's bird habitat. But in the last couple of minutes, I wanted to extend this thinking beyond bird habitat and consider a few other metrics. So in a prior phase of this work, we developed a framework for analyzing scenarios of landscape change like this, using habitat suitability models like these, but also other models and data representing other metrics. And right now, what this framework looks like is an R package that's freely available to download and use. It's been developed specifically with the Delta in mind and incorporates local data and models to support evaluating multiple metrics. And these metrics are grouped into 4 main categories of benefits relevant to the Delta Plan goals. And within each of those categories, we identified multiple metrics for which at least some data was available to incorporate into this framework. It's definitely a work in progress, and we hope to continue developing it. But for now, biodiversity support so far is just represented by habitat suitability models for a few different groups of birds, but could definitely be expanded to include other species and models that you all are developing. Agricultural livelihoods includes both gross production value and the number of ag jobs and their wages based on publicly available data. Climate change resilience is a qualitative score representing the ability of different land covers to tolerate extreme events of heat, drought, and flood. And then also landscape diversity as sort of a broader indicator of resilience. And then water quality is represented as the risk to water quality from pesticide application rates in a few different groups of pesticides, as well as nitrogen loading rates. So we applied this framework. We also applied this framework to each of these tidal restoration scenarios to estimate net changes in each of these other metrics. And again, similar kind of just high-level summary here. In contrast to the changes in habitat we saw, here we find very little difference across scenarios and alternatives. For ag livelihoods, we estimate small but not statistically significant decreases regardless of scenario. And for water quality, small benefits. And both of these were really the result of converting some ag land covers to either tidal wetland vegetation or open water. And then for climate change resilience metrics, we estimated a significant increase in overall landscape diversity. So again, the idea with this framework is that we can quantify and visualize co-benefits and trade-offs of landscape change scenarios across multiple goals. And we'll be updating this R package with these new tidal wetland bird models to make them accessible to incorporate into future scenario analyses. So a few take homes to leave you with from this work. One is that restoration extent matters for birds, at least, with more significant gains expected with scenarios 2 and 3, and really going beyond the restoration that's currently planned and in progress. We didn't really find any location effects, so not much difference between scenario 2 with more work in the Delta and scenario 3 with more in Sassoon Marsh. But the restoration design really matters, of course. So large differences between the A alternatives with less vegetation and the B alternatives with maximum vegetation. No statistically significant trade-offs estimated with an asterisk because here we only examined tidal wetland restoration in these scenarios, which have a relatively small footprint on the landscape, but trade-offs might accumulate as all of the restoration projects are combined. And then, of course, we haven't evaluated all possible metrics of interest. So it would be great to incorporate models representing other species and ecosystem functions. And in our case, we're particularly interested to see the potential trade-offs to birds that use non-tidal wetlands that might be, if some of those were to be converted to tidal. And then finally, we think this modeling approach is helpful for informing restoration and landscape scale planning. And so please reach out if you have scenarios in mind to evaluate or other ideas for expanding on this framework. We're all about collaboration. So thank you all for your time and attention, and especially to Prop 1 funding through CDFW for both phases of this project. And then I'll say we're also extremely grateful to many people who shared data, helped with site access, and offered some input on this project. Thanks, everybody.
Thank you, and we'll have time for 1 to 2 questions.
Thanks, Kristen. Interesting study, great presentation. I'm wondering if you have considered looking at the Virginia rail, and I wondered if you had any guesses as to whether maybe some of those rare marsh species that you've already looked at might have sort of similar or differing responses in the habitat models.
Yeah, it's a good question. We haven't looked in specifically into Virginia rail. I believe they're detected in some of these surveys. The idea with the selecting focal species is that you hope they're they're representative of a broader group of species. Of course, they're all unique in their own way, and it would be great to build models for them all. But yeah, it's a good question. We could always add we add more with more time and more funding.
Well, I've got a question for you.
Okay.
I'll just reach over here. What was the sea level rise conditions that were built into this?
Yeah, thanks for bringing that up. We completely ignored sea level rise, and that is a choice that we made, and mainly because the scenarios we evaluated, you could forever make them more and more complex, right? And consider all of the different variations. So we used existing DEM data or recent DEM data to kind of define where we thought open water would be, but did not try to look into the future as far as projections of sea level rise or projections of what adaptation measures might be taken to deal with some of that, or to try to model sediment recruitment or all of these other things that you could do to make it a much more complex a modeling exercise. What we really wanted to do was just kind of get some bookends and consider the range of possibilities to explore these different different amounts of restoration and different kind of emphasis in different places. But for sure, considering sea level rise will be really important to getting much more accurate projections of actual sea level rise. But likewise, we'd want to include actual restoration plans for these individual sites that reflects what people are actually planning to do. Good. All right, thanks.
Thank you. Thank you, everyone. We will have an extra 20 minutes for lunch, so there's lots of time to talk to the speakers individually, to ask questions. Please be back here at 1:10 for the afternoon sessions. As a heads up, there's a couple food trucks that are scheduled to be outside: Allen's Barbecue and Burgers and the Fry Boys Burgers. Thank you. All right, if everyone could make their way to the seats, we're gonna get started soon.
There we go. All right. Thanks, everybody. Let's all have a seat and get started. Appreciate you all coming back after lunch on a pretty warm day. But I think I have the antidote for post-lunch sleepiness. We've got 3 great talks coming up. As you would expect from the session title, we've got a broad array of topics, from the impacts of fire retardants and pesticides on salmon to a more broader look at collaborative institutions for modeling in the Delta. So without any further ado, our first speak is Amelie Segarra from the University of California, Davis, who's going to talk about the impact of fire retardant on salmon.
So good afternoon, everyone, and thank you for being here.
especially after lunch. So I'm Amelie Segarra. I am an assistant adjunct professor at UC Davis. And today I will present a study that was part of a broader project in collaboration that was performed in collaboration with Dr. Susan Brander from Oregon State University. And so the project is about assessing the lethal and the sublethal effect of fire retardant on early life stages of salmonids. So as you might already know, wildfires are becoming more intense and severe due to climate change and landscape mismanagement. And the top graph here shows an increase of the amount of land area burned per year. And with this increase, we see an increase of fire retardants that are used. For example, phosphate, which is a fire retardant. So those fire retardants that are called long-term fire retardants are very efficient, and they are broadly used, and they can be one single product can be used for to contain a fire, so during an active fire. But the same product can also be used as a pre-treatment, so even before a wildfire. And so, as you can see on the picture here, the truck are spreading the product. And it's applying as a pre-treatment. If you are wondering what is the difference between the colored one and the non-one, it can be exactly the same product, but a dye is added to help the pilots or the firefighter to better visualize the product when it's applied on the ground. I also want to highlight that the pre-treatment is heavily used by the public as a pre-treatment. And you can buy it to protect your house. It's PFAS free. I really want to emphasize that because most of the time when we think about fire retardant, we think about PFAS. Here it's not the case. Those fire retardants, the main ingredient is ammonium polyphosphate. So basically it's a fertilizer based. And so the environmental concentration are poorly characterized. Mostly because when this active ingredient enter in the aquatic system, it transforms into ammonia and phosphorus. So as you know already, the ammonia will be directly toxic for the fish and can alter the behavior, reduce growth or development, for example. And phosphorus will have an indirect effect by altering the ecosystem through eutrophication and reduce the oxygen level. So basically, those two nutrients are already present in the environment as a background. So there are regulations to avoid to apply the product nearby the water bodies. But in emergency situation, and especially when human population is at risk, then an accidental drop-off can happen, as you can see on the two pictures here. Okay, here and here. This product can also enter into the aquatic system during a cleaning process, but most likely they will enter in the aquatic system after or during a first flush and a runoff event. So now the first flush event often overlap with the salmonid spawning season. And some salmonid species are already described as a species of conservation concern here in California, such as Chinook salmon. And more, in parallel of that, the early life stages are also often described as being one of the most sensitive life stages. So there is a high risk for aquatic ecosystem here. Now, another thing to know about these fire retardants is that they are very sticky. They can last for several months on surfaces. And so from the first application to the first flush, the product might be exposed to different environmental conditions, such as sunlight and heat. And so this weathering process might alter the toxicity of the product. And so with that being said, the aim of our project was to determine how and to assess how do fire retardant impact the early life stages of salmonids in the context of weathering process. So for that, we used two different species and two different life stages.
So we use rainbow trout at Oregon State University and Chinook salmon at UC Davis. And we used embryo and alvin as early life stages. When we started, we only knew the LC50 for rainbow trout juveniles. And so we really wanted to assess how toxic it is for the early life stages. Today, for the talk, I will focus on Chinook salmon embryos. And we tested different fire retardant, but because of time matter, I will show you the first data we obtained using one single fire retardant. So these exposures were led by Dr. Kominasi, a postdoc in my laboratory. And so she first assessed the lethal toxicity. So she did a standard 96-hour aqueous exposure on Chinook salmon eggs. For that, she used a Foschek LC95W, which is commonly used for wildfire, but also publicly available and used as a home defense. So we were able to buy this product from Home Depot. She had two different treatments, the non-weathered, which correspond to the freshly applied product, and the UV weathered, which correspond to 1 year of UV light exposure. So basically for the second treatment here, we took a part of the product and we processed the product using a solar simulator. She had different or multiple concentrations for these two treatments, including a control. And after 96-hour exposure, she assessed the LC50, which is the concentration at which 50% of the population will die. So here you have the dose response curve for these two treatments, and the table is a summary of the data for the LC50. So as you can see here, the LC50 for the weathered treatment is around 15,000 microliter per liter, and it's much lower compared to the non-weathered treatment, which is around 35,000. So basically we need less product from the weathered treatment to kill 50% of the population. So the weathered treatment is more toxic than the non-weathered treatment. So we are currently doing a non-target analysis to better understand the differences we see here and potentially identify a chemical transformation. Now, at Oregon State University, they assessed the LC50 for rainbow trout. And as you can see, here the LC50 for this species is much lower compared to the Chinook. So rainbow trout is much more sensitive than Chinook salmon embryo. We are currently working on analyzing the data for the juveniles. To put these numbers in some context, so the recommended application mixture of this product is 167,000 microliter per liter, which is the final concentration that people will use, or final concentration that is applied on the ground. Obviously, those are terrestrial application, right? So we expect to see dilution when this concentration will end up in the aquatic system. But to give you an example, a dilution of 1,200 time will still correspond to 50% of mortality in rainbow trout embryo. So let's go back to our Chinook salmon embryo. So with this LC50 that Dr. Kominasi determined, she was able to calculate and use the lower concentration to assess the sublethal toxicity. So her concentration here goes from 50 to 3,200 microliter per liter. And so she did exactly the same type of exposure, meaning the standard 96 aqueous exposure to assess the sublethal toxicity here using the two different treatments. And again, because here we wanted to assess the sublethal toxicity, we kept the fish in clean water to assess different endpoints, such as the hatching success, morphology, and looking at also different behavioral endpoints. Today I will focus on the behavior part. But I just want to highlight that the behavior happened 46 days after the 96-hour exposure, which is the time when the fish were starting to swim in the water column. We also looked at the mortality over the entire experiment. So before I dig into the behavioral data, I want to show you the mortality. So as expected, we had no mortality or no significant mortality across treatments and concentration. However, we had we were surprised to see significant differences, especially for the weather treatment at the 2 highest concentration, even after the experiment. And so here again, we confirm that the weather treatment is more toxic than the non-weathered, even at lower concentration. So now let's see the behavioral data. So to have an overview of the routing locomotion, Dr. Kominasi measured different parameters. She measures the total distance moved, the velocity, the freezing, the cruising, and the bursting for both treatments. And on the bottom, you have the different concentration, including the control. As a reminder, the 2 highest concentration for the weather treatment, we had 75 or more % of mortality. So we don't have any data for these 2 highest concentration. And so for the color, red means that the value for a specific parameter is higher compared to the control, and blue lower compared to the control. And any star represents significantly differences compared to the control. So I know it's a lot of colors, it's a lot of stars. And so let me help you here. We have an increase of freezing and bursting, but we have a decrease of cruising almost across all of the concentration for both treatments. So basically, we are seeing a hyperactivity and erratic behavior compared to the control. So basically, the exposed fish are swimming like that compared to the control. So the take-home message here is that the embryo exposure causes persistent alteration in alvin locomotion, even 46 days after the exposure. And so any kind of alteration in terms of behavior can have potential impact, such as reducing foraging efficiency and increasing the vulnerability to predators. So when we put our results in context, we see that the recommended application exceeds the laboratory LC50 and sublethal data that we obtain at the embryonic life stages. Our results also suggest that the environmental weathering might increase the risk to early life stages. There are concerns regarding the chemical compositions that I also wanted to mention. Indeed, when we just finished to expose our fish, a paper was published saying that there is metal present in the same product, which was not mentioned by the manufacturer. So soon after that, the product was phased out by the US Forest Services, and there is replacement product. We already started to work on this replacement product to compare both the phased out and the replacement product. I mentioned earlier that there is also accidental drop-off that can happen. And one study, a very recent study, highlights that the phosphorus can persist in sediment and be transported downstream up to 6 kilometers for up to 1 year during this accidental drop-off in the stream. And I want to mention again that the environmental concentration are poorly characterized. We need more data to better link the thresholds that we obtain here to what really happened into the field. But there is, looking forward, there are several directions that could help improve both our understanding and management of fire retardant exposure in aquatic systems. So first, improving operational practice could help reduce risk of fire retardant entering in the aquatic system. So this includes improving aerial drop, accuracy and planning near the sensitive aquatic habitat. Second, a targeted exposure monitoring could better characterize environmental concentration. This could include water quality monitoring near the fire retardant application, either pre-treatment or to contain a fire, or both, obviously. And also measuring ammonia and phosphorus before, during, and after a fire retardant application, including first flush event. So this before data is very important to determine what is the difference between the background level versus the pulse that we can observe in terms of ammonia and phosphorus. And so we can leverage our existing monitoring data set to better distinguish the background and the pools that I was just mentioning. And finally, it is important to better characterize and understand the species sensitivity. Again, we saw that rainbow trout is much more sensitive than Chinook salmon for embryo life stages, what is happening to the other life stages, but more importantly, the question is remaining regarding other species, such as steelhead. I'm sure you all thought about steelhead since I'm talking about Chinook salmon, and also the delta smelt or longfin smelt. And with that, I would like to thank the UC Davis department and all the firefighters. I would like to thank my lab, especially Dr. Luis Cominassi, my collaborator, Dr. Bonder Susan and her team. And of course, I would like to thank the Delta Stewardship Council who funded the project. I think I have time for questions.
We can do maybe one quick question. All right.
Okay, thanks.
Thank you. All right. So our next speaker is Professor Michael Lydy, and he's going to be giving a talk about pesticide accumulation in juvenile Chinook. That was originally going to be his postdoc Hadis, who was unable to travel today, but this is her presentation that he'll be doing. So, oh, there we go. Oh yeah, here we go. That's supposed to go close, and then there we go. Thank you. All right, you're good.
Thank you guys. I appreciate the fact that you guys have had wonderful weather the last few days. I left Illinois, it was a blizzard, so it's a pleasure to be out here. This is a collaborative project that's been going on for a few years between the Segarra lab and ours at SIU. I want to thank Jake Stagg and the U.S. Fish and Wildlife Service for providing fish for the project. It's been incredibly helpful. We had also acknowledged our funding, which came from the state water contractors and the Metropolitan Water District of Southern California. This group already is well aware of the fact that the Chinook salmon populations are obviously in decline, and multiple stressors act upon those fish during outmigration. Altered habitats, managed flow regimes, temperature stress, predators, and what I'm going to focus on, contaminants have impacted those populations. I've worked in the Delta for about 2 decades. Much of that work's been with my good friend Don Weston, and what we've seen time after time after time is the same contaminants are the main players. They're found in the water, they're found in the sediment, the prey, the fish species. These include things like the pyrethroids, some of the newer phenylpyrazoles, and some of the organochlorine pesticides. In a study that was a little bit more recent, done by one of my grad students, Sarah Anzalone, she looked at pesticide residues specifically in juvenile Chinook salmon and their prey in riverine and floodplain habitats, and found the same thing Don and I've seen again for decades. And that the main players were bifenthrin, a pyrethroid insecticide, fipronil, which is a phenylpyrazole, and its 3 metabolites, sulfide, sulfone, and desulfonyl. Those are important because they're as toxic, or if not more toxic, than the parent compound. And then a degradation product of DDT, 4,4' DDE. So that was the focus of this study. So objectives were to assess spatial and temporal differences in pesticide concentrations in juvenile Chinook salmon as they outmigrate. We also deployed field deployed or caged salmon in specific locations to look at specific exposure issues. We then related the pesticide concentrations in these fish to effects predicted by some of the models I actually talked about last year, which are response spectrum models, which I'll again introduce today. And then finally, at the end, I'd like to link some of these results to possible management decisions. So the hatcheries released, in the order of 38 million fish. And the hatcheries we worked with are Battle Creek, Feather, Nimbus, Moke. And when these fish are released, many of them have, as you guys know, coded wire tags associated with them. Because they have those tags, we know where their release point is and where their collection points are. So we know residency time in the system, and we have a sense of where they've migrated through. Then groups like Jake's at the Fish and Wildlife Service and other agencies provide us with the fish. Groups like Amelie go and cage the fish in the system, and we then compare those residues again to some of our models. For our field caught fish, we collected 314 samples, which represented 510 individual fish. Some of the fish are small enough for chemical analysis we had to composite them. They were done over a 4-study year period from 22 to 25, and they included all 4 runs, late fall, spring, and winter. There were multiple release and collection points in the system, and those are noted on the slide on the map. The residency times range from 1 to 118 days. For the caged fish, we had 77 samples. They were collected in June of 24 and in the rainy season of 25. There were 5 sampling sites noted in the X's on the screen, and these exposures went from 12 to 15 days. When we received the fish at SIU, we did whole body homogenate doing freeze-dried tissue. We used a catcher's technique with the lipid precipitation and other cleanup before we did GC mass spec. All the values are lipid normalized, and the values are reported on a molar basis to allow for easier comparison across compounds. So here's some of the data. On the left is the bifenthrin data, and on the right is the DDE data. The y-axis is the concentration in the fish, either caged or in the field collected fish, on a nanomoles per gram lipid basis. The x-axis is the residency time in days. Again, the yellow circles represent the American River, the open circles are Battle Creek, the blue are Feather River, the pink are Fremont Ford Bridge, which is the San Joaquin, and the green are the Sherman Island net pens. First thing you notice is that as residency time increases, we get an increase in the residues of both compounds. The other thing that's notable is there's some outliers, much higher concentrations. Those are the ones notable from the Feather River and in the San Joaquin. I'll get back for reasons why we think that's happening a little later in the talk. One thing you note is that fipronil is not on this list. If you look at the fipronil data, it's a little different, followed a different trend. In this one, in this bar graph, I'm showing you the average fipronil sum, so that's parent plus metabolite residues in the fish. On the y-axis and on the x-axis, I've got time from 22 to 2025. The bars represent the average fipronil sum concentrations. The numbers represent the detection frequency. And so from 22 to 25, the detection frequency in the fish went from 22% down to 0, right? So a precipitous drop in the fipronil concentrations in these fish, which is incredibly surprising because, again, Don and I'd seen this to be a very problematic class of compounds, in particular fipronil, for over 2 decades. So again, I'll get back to that in a moment. Specifically looking at the caged fish, again, these were controlled experiments. We placed them in specific positions in the watershed to address specific questions. The caged fish overall showed about a 5-fold increase for DDE and a 6-fold increase for bifenthrin compared to control fish. Remember, these are in 12 to 15-day exposures. These fish that are used in the cage are coming directly from the hatcheries. We measure the concentration in the fish when they come from the hatcheries in addition to their food. They do have low levels of DDE in the hatchery fish and in their food, but the increases are significant in that 2-week period of time. One interesting thing is the residues we found in the caged fish were very similar to the concentrations we found in the free-ranging fish, which again we found surprising because the caged fish are going to be a little bit more limited in their food resources, at least that's what we thought. So the bottom line is that the accumulation for as little as 2 weeks creates a significant risk to these fish exposed in these systems. We then did multivariate analysis on the bifenthrin and DDE data. So we used combination of the following factors: residency time, run, release site, collection site, study year, hatchery, and distance traveled. The bifenthrin best fits were residency time plus release time plus run. The DDE fit were the same with the addition of the collection site. The data is over on the left-hand side. Basically what I'm showing is the predicted log bifenthrin on the Y and the observed log bifenthrin on the X. The lines represent the one-to-one relationship, and you see that fits quite well. So the conclusions from this data set is that longer residency times lead to higher residues, right? Which intuitively kind of makes sense, right? Release site factors suggest that some migration pathways cause higher exposure than others. The two that we found is, again, the San Joaquin and the Feather River were elevated much higher than the other parts of the system. We also found that fall fish, March through May releases, have higher bifenthrin than late fall fish with an earlier release from November to January. It's most likely for bifenthrin in particular because it's a current use pesticide. It's coming off during the rainy season. And then higher DDE residues in salmon were collected at Chips Island, which is our most downstream site, suggesting that downstream exposure is important for DDE, probably more than other parts of the watershed. Okay, so we have the data. What does this mean in terms of effects in fish? Again, last year I talked a little bit about our response spectrum models. These are in-lab studies that were done, again, in collaboration with Amelie's lab, where we did aqueous exposures to salmon, they were par, and looked at residues in the fish and then related those to specific effects in those fish. So for example, this x-axis is bifenthrin residues, again, on a nanomole basis, and this residue, about 0.4 nanomoles, represents a concentration in the salmon where we'd expect shoaling and locomotion effects. At slightly higher concentrations, we'd expect anxiety effects, and then at higher concentrations, growth, swim performance, upper thermal tolerance, olfactory responses, and as you would expect, lethal residues are much higher, or at least residues required to achieve lethality are much higher. If we place our data, especially the data that's from the Feather River and the San Joaquin, the concentrations are high enough by themselves to impact outmigration success, or at least the shoaling and locomotion behavior. In addition to the single compounds, we've done mixture experiments, and in those experiments found more additive effects, and therefore we'd expect greater than additive response in terms of an effect in these field-caught fish. So if you relate this to predation, if you look at predation by piscivorous fish as being one of the major stressors on outmigrating juvenile Chinook in the Delta, and the problem's getting worse, we're suggesting that the internal pesticide loads that we're seeing in these fish is actually changing their behavior and increasing the risk of predation in the system. Based on our current benchmarks, that would impact something in the order of 380,000 fish. And again, I've showed you striped bass that consume lots of juvenile Chinook. So these findings suggest that, one, internal bifenthrin residues, again, are high enough for them by themselves to cause locomotion and shoaling effects, which could impact the success of juvenile Chinook as they outmigrate. Mixture effects are important, and we expect greater effects due to additive responses. If we look at the mixtures themselves, the effects are due mostly to bifenthrin, about 80%, with less impact from DDE. And again, it was very surprising that fipronil was found at very low concentrations, and there were fewer detects than we expected, and therefore it did not play a major role in terms of the mixture impact. The migration timing and season impacts pesticide accumulation. And again, I want to spend a little bit more time on these last 2 points. The Feather and San Joaquin are an issue, and that they have much higher residues associated with those fish. Therefore, the route that these things outmigrate is going to be important. And then finally, kind of a success story potentially, the fipronil residues in the fish dropped over the last 4 years, which is due to maybe a labeling change that was done with a re-registration in 2019. So again, a little bit more about these. So why is bifenthrin exposure elevated in the San Joaquin and the Feather Rivers? The San Joaquin is well known for its contamination issues originating from urban and agricultural land uses. And some of the work that Don and I've done has shown that. Total maximum daily loads, or TMDLs, are already in place for a watershed-wide control program, which includes the San Joaquin. So the state understands there's issues and is taking progressive actions to try to correct that. The Feather River is different. Feather River is less studied, and it was a bit of a surprise to us, and maybe some of you, to find issues associated with the system. So we started exploring where could bifenthrin be coming in the Feather River. And so we started by looking at the bifenthrin usage in that watershed. This is kilograms of bifenthrin used over a year from 2015 to 2022. And you see the majority of the use is ag-based, and 87% of that ag-based is walnut and the almond industry, okay? When I think of bifenthrin in the state of California, I think urban, right? So this was quite different for me in terms of a bifenthrin signature. And so we then looked at the orchards and the progression of more orchards being introduced since 2008. So 2008 is the one here, and this is the Feather River. And we also looked at the map in 2023. There was I should mention the walnut or the green, and the orange are the almond production. So there's about a 61% increase in walnut and over 100% increase in almond production over that period of time. Also, these crops tend to be right on the river, right? And so there's a possibility that you have bifenthrin entering the system from these crops. So we question whether is runoff from irrigation or stormwater in these fields an issue. I've shown you on the screen an older orchard that is actually flooded for irrigation purposes. If you have bifenthrin that's been applied recently, then you're obviously going to get a dose of that into the water body. You can also have spray drift, timing of spraying, especially during the dormant season. That can be a real problem in the orchards. And orchards overall lack BMPs to a large extent. They don't have cover crops. They don't have anything that prevents the water particles and bifenthrin from moving off site. And so we suggest that that might be an issue, or at least a source. So about inputs from tributaries. If you look at that system, again, less biomonitoring and water chemistry has been done over the years in the system, in part because it's deemed to be, fairly clean system. And so we started looking at the databases, and the Yuba is the only place we could find previous data that suggested bifenthrin exposures in sediments. And there were hits below the dam at the Yuba Dam. And so, I should point out that we placed cage systems up near the Orville area and then down below Yuba. And the fish below Yuba had much higher residues associated with those caged fish. So there'll be a strong suggestion that there may be a source coming from the Yuba in addition to potential orchards above. So what are the potential options for assessing the extent of this problem? Obviously, you need to perform monitoring studies to better get a better idea of overall potential contamination and what the sources are. Then it may need a pesticide-related TMDL if the problem is bad enough to be developed for a corrective action for the waterway, and maybe a 303 delisting if it's deemed to be enough of a concern. All right, let's go a different direction. Fipronil. Why are the fipronil residues actually dropping? In 2017 to 2019, there was a re-registration that resulted in label changes in the liquid fipronil applications for products like Termidor. These restrictions applied to the landscape and structural application industry, and it restricted applications on impervious surfaces, including up on houses up to like a foot and a half up to the foundation of the house. It also prohibited outdoor applications from November 1st to February 28th, which probably made a huge impact. For the state of California, there are only two certified and regulated application types, and one is structural and landscape. The other one is pet industry, okay? And so keep that in mind. When we're looking at, again, my data, again, these are in salmon over a 22 to 25 period. We saw a precipitous decline in the fipronil levels in those salmon across all of our sampling locations. We then looked at DPR databases, and they had information on the detection frequency for fipronil, sulfone, and desulfonil from 2008 to 2024 throughout the state, especially the northern part of the state. You can see declines in all those parent and the metabolites for their studies, and those are, again, water studies. We also look at the usage, and this is in kilograms in the system of fipronil, and you can see this is from 2015 to 2022-ish, and you see a precipitous decline in the amount of fipronil, and then it stables off at a much stabilizes at a much lower level after the 2019 registration. Note that the data I'm showing you here is just for the pesticide landscape group, so for that industry, because they are required to monitor this. So they give us very good records in terms of the usage. The pet care industry does not have this requirement, and therefore I'm not recording that as part of this, okay? The state of California has, however, deemed the pet industry to contribute to the problem. It's coming from pet salons. There's been a number of studies showing pet salons, and the effluent coming from it gets to sewage treatment plants and are a problem there. And so in December of 2025, so just a month or two ago, there was some suggested action for the pet industry to effectively remove all over-the-counter products like Frontline from stores, right? And so you're going to have to go to your veterinarian to get these products. And, you know, after our data set, I started thinking, you know, do we really need additional restrictions? I'm not saying the pet industry is not part of the problem. What I'm saying is we're making a huge impact by just what they've done with the other professional applicators, that maybe restrictions need to be considered or maybe not. And so I leave you with a thought, and that is residue data like ours, I would argue, can be used as an integrated measure of exposure to address some kind of interesting questions, like some of the management decisions and questions I've just posed. I'd love to answer any questions you have at this point.
Okay, I think we have time for one question.
Yeah.
You had caged fish out there for 120 days, salmon?
We had caged fish for 12 to 15. We had caged fish from 12 to 15 days. The field caught fish were ones that the U.S. Fish and Wildlife Service caught for us, and we were able to track their length of time in the system based on their PIT tags or the tags.
Okay, I misread your graph then. Thank you.
Yeah.
Thank you. All right, so the last talk in our session before the break is by Michelle Stern from the Delta Science Program, and she's going to be talking about the new Delta modeling, keep calling it a conservatory, that's not it, collaboratory.
Thanks, Ted. We're kind of switching gears a little bit. This is a water quality session, so thanks for having me here, but we're gonna kind of zoom out a little bit and talk a little more generally about modeling. So my name is Michelle Stern. I'm a senior environmental scientist here at the Delta Science Program. I'm new to the agency since October, and I previously worked as a hydrologist at the California Water Science Center and USGS. It's really nice to see some of my colleagues here. My background is in watershed modeling and looking at the effects of climate and land use change in water quantity and quality. So today I'm going to be talking to you about modeling the Delta together, foundations for a Delta modeling collaboratory. And I mess up the term all the time, so. So I want to start by talking about a project that might be familiar to some of you. It was inspiring and formative to me as an early career researcher at USGS, Cascade, or computational assessments of scenarios of change for the Delta ecosystem. Cascade was led by Lisa Lucas and Noah Knowles at USGS, and they brought together a diverse group of scientists, modelers, data managers, and stakeholders to answer complex management questions through climate change scenarios. And the main question that they wanted to address was, how will future changes in physical configuration and climate affect water quality, ecosystem processes, and key species in the Delta? So on the right, you can see the conceptual model linkages. And central to this project's success and difficulties was using this linked modeling approach. That meant that each of the models were interconnected, starting from the climate models at the very top, all the way down to the fish and marsh accretion models. And I was responsible for the watershed modeling that produced hydrology and sediment transport. And that got fed into the hydrodynamic structure that's on the right, shaded in blue. So at the time, I didn't realize how much work actually went into bringing a diverse group together, regularly coordinating inputs and outputs of different models so that they fit together, and talking with stakeholders to identify relevant scenarios. And that was all in addition to the technical modeling work that we did, which was already a lot of work, as you already know. So I kept thinking to myself, how do these research scientists get so good at facilitating to complete our common goal? Some of you might know this isn't really part of our standard training as modelers. And so I came to understand that these soft skills are essential to moving together these complex projects. And it comes more naturally to some than to others. And looking back on this project now in my new role at the Delta Stewardship Council, I can't help but think, could Cascade have been even more impactful, more successful, and faster if it had a stronger support network and access to existing, relevant, and shared resources. So I'm a rower and I love a good sports analogy. And I had to add in a photo of, in my opinion, the most collaborative sport, which is rowing. When one person is out of sync, it disrupts the entire boat and you can't go very fast. Collaboration is all about understanding who you're with and continually adjusting so that together you can achieve your common goal. I definitely do not have to tell this group in the room and online about the benefits of collaboration. If you're here, you're already doing it and you have been for a long time. And as the saying goes, if you want to go fast, go alone. If you want to go far, go together. This is repeated for a reason. Scientists and practitioners already know the value of collaboration and how it can increase the impact and usefulness and the outcomes of your research or your project. Think about the most wide-reaching studies and initiatives. They tend to always rely on multiple agencies, academics, nonprofits, and stakeholders to guide the results into a useful product with lasting impact. So by now you may be asking yourself, what do we mean by collaboratory? Let's get into it. But first, I am going to ask you to take out your phones and please scan the QR code. If you haven't done a Mentimeter poll before, just scan the code or put in that code if you are in a browser. So please join us and take our first poll question of 2. There's only 2. When you hear the word collaboratory, what does that mean to you? And I will start off with a simple dictionary definition of a networked organization in which scientists can collaborate, or a research center without walls. So please type in your short definition and we'll try to look at the results together. I don't know if this is going to work. Doesn't look like it. We already have a lot of results. I'm just going to read some because I don't think it'll show up on that screen. Can you see the results coming in on your screens? No? Okay. I'm going to read a few of them. Wow, we got some really great responses. IEP, complementing others' work, a center to facilitate collaboration, working together is a really common one, collaboration, think tank. Yeah, all really great responses. Keep them coming. Synthesis, love it. Okay. So now that's a good transition. Well, next I'm going to talk about how we are thinking about the word collaboratory and comparing that to collaboration. So what is a collaboratory? We are defining collaboration as the general, unstructured, active process of people working together toward a common goal. In contrast, we have collaboratory, which we're defining as an inclusive network of shared digital tools, data, and other resources to facilitate a collaborative research toward a common goal or problem. So you may have noticed that there's already a lot of great examples of collaboration out there, including IEP. Some that may even seem to overlap with the collaboratory definition. These questions have been brought up by many people in the Delta modeling community. Why do we need a modeling collaboratory? I would start with modeling takes place at many agencies, academic institutions, and private entities that are often pursuing different questions. And even when you're using the same model, different conclusions can be made due to different scenarios, different assumptions, or different data used by the individual models or institutions. Further, it's difficult to exchange information between the discipline-specific models necessary to address many contemporary questions. If we think back to the cascade example, I had to produce outputs from my model that went into another model, which was a hydrodynamic model. So we had to coordinate different parameters, time steps, and make sure that everything worked together properly. And that took more time than I think anyone thought it would. I have often found myself over the years wondering if someone else is modeling the same thing that I'm modeling, but for a different question or a different purpose. And sometimes the answer is yes. And if you're working in the Delta, it's almost certainly yes, right? And so how does this happen? One of the things that I'd like to bring up is siloing, the institutional barriers between and within the many federal state agencies, academia, and consultants, which means that we don't always talk to each other or know what's going on in what other efforts that are going on. This is especially troublesome in a complex, interdisciplinary space like the Delta. It's not always easy to keep up with all the modeling efforts that are happening in adjacent but related fields. I think importantly, agencies and institutions have various levels of resources and institutional support to devote to modeling, and each modeling project generally relies on separate resources. What if there could be a new starting point that would leverage the expertise and information from the community to help level the field for modelers and collaborative modeling projects? So the Delta Modeling Collaboratory purpose is to enhance collaborative activities between modelers and non-modelers alike, as well as share curated input data, scenarios, and results, support data streaming between different models, and to provide training and collate existing resources. In the end, the goal is to support a modeling community that is at the forefront of predicting the outcomes of water and environmental management scenarios. And if you can see this infographic on the bottom, we have our complex socio-environmental challenges, and then we can envision the Delta Modeling Collaboratory kind of providing these shared resources that actually translates into usable science for decision-making. So I want to discuss conceptually how a collaboratory may support ongoing modeling efforts and enable more impactful research. First, we can look at a common 2 to 3 year project timeline that a lot of you are probably already familiar with. We start with a study question, a modeling approach, data exploration, data QA/QC, and then the modeling and data analysis. And then finally, we move on to publish our reports and our data and communicate our findings. Now, ideally, the team is able to promote their work to the science and management communities for maximum impact. But unfortunately, it's not uncommon for teams to run out of time or funding. And ultimately, the things with the highest potential to increase the impact and reach are often remaining at the end of the project when you no longer have time or resources to devote to them. We've all been there. So now if we look at a common 2 to 3 year project within the context of a collaboratory, we can think about some of the potential shared resources and benefits that could improve efficiency and impact of your project. Some of those things we're envisioning are cloud computing resources, networking, a data librarian, QA/QC data, facilitation, an online modeling forum, publishing and visualization assistance, as well as training and workshops. So we propose that the addition of these shared benefits would enable the Delta modeling community to answer complex management questions in a more supported, efficient, and impactful way. And these resources would be consistently available, importantly, instead of project by project and institution by institution. Okay, time for our second question. Now that we've defined collaboratory and its purpose, I'd like to open this up to the audience to see what tools you think are worthwhile for encouraging collaboration. What benefits would make your time cost more worth it now because of speed, or to be more efficient later? So examples again might include cloud computing, a data librarian, things like that nature, but I really want to hear about what is impactful in your workflows. What would make that easier for you? And we'll see how those results line up with our working group. Let's see. Are we there? Give you a few seconds. Oh my gosh, amazing. Okay, we have long-term data, data access, database, let's see, historical data sets, GIS, DSM2 calcium dataset, cloud computing, wetland mapping. Okay, I love it. These are all amazing. Some really good suggestions here. So we are going to put this in context of some of the work we have been doing here at the council. So in 2025, the Delta Science Program launched 3 working group projects to assess the feasibility and value of applying a collaboratory supported modeling approach for 3 different groups. So we have the modeling and predicting cyanobacterial harmful algal blooms, or CHABs, evaluating salinity intrusion and associated management actions, and restoring tidal wetland food webs. And these are our 3 groups. And these 3 working groups were chosen to represent a non-exhaustive selection of modeling challenges facing decision makers to demonstrate a proof of concept for the Delta Modeling Collaboratory. Instead of designing a modeling study based on a management question, like you would typically do, these working groups were tasked with identifying common models and approaches, shared needs for data and baseline conditions, scenarios relevant to multiple management needs, and opportunities for training and knowledge transfer. Operating these projects in parallel provides opportunities to identify synergies between projects, facilitate resource sharing, and prioritize investments that support multiple initiatives. Through the working group process, we met regularly across all 3 projects and included individuals who were actually tasked with drawing connections between the groups. So let's see what the groups have found so far. During this process, we asked each group individually to list their own resource needs relevant to their modeling workflows to accomplish short-term, long-term, and the moonshot type goals. We compiled those needs into a Venn diagram to identify what kind of emerges as commonalities between these 3 groups. And around the outside of the Venn diagram, you can see the resource needs that were useful for each group's specific management workflows. And some of those things were hydrodynamic model data, decision support tools, and remote sensing data. As you move closer to the middle of the diagram, you see common needs across multiple groups. And then in the middle of the Venn diagram, we can see that funding, not surprisingly, curated QA/QC data, bathymetry, and digital elevation models were identified as shared resource needs across all three groups. Is this finding surprising to you? Could you also use these resources in your projects? We can think back to the resources you identified in the second Menti question. And if you have any more suggestions, please feel free to contact me about them. So the next phase of this work will implement approaches identified during this initial profiling phase, which is currently ongoing, but wrapping up soon. Based on the profiles and other feedback we've been gathering, we are writing a white paper that synthesizes the cross-cutting results from each group and charts a path for the envisioned collaboratory. This could include facilitating communication and exploring funding options, as well as actually conducting and modeling and the data analyses for one or more of the groups. That could become the first collaboratory supported project. So in conclusion, the vision of the collaboratory is a networked community and shared system of modeling resources that add value and support a range of collaborative modeling. The collaboratory would also provide support for integrating models and data sources to provide actionable insights for managing environmental and water resources. And the next steps do include a white paper synthesizing the working group results, so be on the lookout for that. We really hope that you'll join us to help grow a stronger, more connected modeling community. And I really want to thank, first of all, everyone who contributed to this talk, and thank you all for your attention and participation, as well as the leadership of Lisa Marie. Thank you. And I want to end with this. In some ways, the Delta modeling community has come a long way since Cascade, right? But in other ways, like the reduction of federal funding and the shifting of research priorities, or the ever-increasing number of models or AI models that are being produced, we need to support this community more than ever. The concept of the Delta modeling community collaboratory is not new. However, this is just the beginning of the conversation. Our community needs support to tackle the most wonderfully wicked problems in the Delta. And those who are interested in helping to form this community or providing input should please feel free to contact us using either email address on the screen or by finding me at the break in a minute. And with that, thank you.
Right, so I don't think we have time for questions, but please feel free to find Michelle during the break, and yeah, we'll come back when.
Yeah, thanks, Ted.
Hello, everyone. We're going to get started with session 17, which is the phytoplankton, algae, or harmful algal blooms session. Thank you for being here after the break. Our first speaker is going to be Kyle Leathers, who is a research biologist postdoc in the USGS California Water Science Center. He's going to be giving a talk titled Spatial and Ecological Responses to a Wastewater Treatment Plant Upgrade in the Sacramento-San Joaquin Delta. So if everyone can go ahead and give your attention to Kyle.
Great to see everybody here, and I'm glad to share some of my research from the USGS. So, wastewater treatment plant effluent can be very impactful environmentally. Effluent can contain nutrients that can lead to toxicity or oxygen depletion, along with contaminants and pollutants. In the Delta region, we have several wastewater treatment plants, but the largest is the Sacramento or Echo Water wastewater treatment plant located near Freeport. And this has been the largest point source historically of ammonium to the Delta, along with being the second largest wastewater treatment plant in all of California. However, there have been some environmental concerns from elevated nutrients from effluent, and it's linked to environmental issues. One environmental issue that people have been talking about here today is pelagic organism decline, the decline of open water fish species like striped bass, delta smelt, and longfin smelt. This has occurred since the 1980s. And one possible reason for this could be a decline in food availability and phytoplankton that have also declined over a similar time frame. One reason for this could be the invasive clam that other people have mentioned. But another proposed idea has been that there's too much ammonium in the system that could be linked to wastewater effluent. This is known as the ammonium inhibition hypothesis, which proposes two things. First, that phytoplankton preferentially uptake ammonium over other forms of nitrogen like nitrate. And second, that phytoplankton like diatoms grow better when they have nitrate that they use to grow instead of ammonium. This has been supported by several researchers like Parker and Dugdale. The study here that found that bloom events only occurred when ammonium reached negligible levels below 4 micrograms per liter. And there's also been studies that have found that phytoplankton communities can change with elevated ammonium, where elevated ammonium can lead to less diatoms and more cyanobacteria. So if the ammonium inhibition hypothesis is true, then we would expect that there's not only less food quantity available to threatened fish species, but also reduced food quality that's available for them. Thankfully, an opportunity to test the accuracy of the ammonium inhibition hypothesis came around with the upgrade to the Echo Water facility in April of 2021. They implemented biological nutrient removal, which has increased nitrification rates and potentially has reduced a lot of the ammonium in effluent. And this cost nearly $2 billion, however. So it's important to know what kind of environmental impacts this might have if other wastewater treatment plants, both in the Bay Delta and also globally, are interested in environmental ramifications. However, there's uncertainty about where water quality might change because of effluent. Particle tracking models suggest that effluent can have impacts on nutrients all the way out to Sassoon Bay and parts of the South Delta, but it can be hard to track where nutrients are moving given tidal influences and the number of diversions of water within the Delta, as shown by the graphic here. There's also been pushback on the ammonium inhibition hypothesis by some scientists. One study by Berg et al. Looked at phytoplankton, especially diatoms in the Delta, and they found that growth rates could be just as high or even higher for diatoms when ammonium is available compared to nitrate. And James Clarn also had a study where he pointed out that bloom events can cause a drawdown in ammonium and nitrate. And since diatoms and phytoplankton preferentially uptake ammonium first, that could lead to a stronger relationship between ammonium and chlorophyll. But this could be a case of correlation, not causation, if the phytoplankton are driving the relationship. So, faced with this uncertainty, I'm asking in this talk, how has the Sacramento wastewater treatment plant upgrade affected the Delta ecosystem? I'm addressing this through 3 sub-questions. First, at what spatial scale does effluent affect nutrients throughout the Delta? Second, how has the influence of effluent on Delta nutrients changed following the upgrade? And lastly, have phytoplankton responded to shifts in effluent, including changes in their biomass and community composition? For this last sub-question, we have 2 alternative predictions, depending on whether the ammonium inhibition hypothesis is true or not. If it is true, then we would expect a negative relationship between chlorophyll and ammonium at that threshold point, about 4 micrograms per liter. However, if it's false, then we might expect a positive relationship where more nitrate can benefit growth and it lead to higher chlorophyll or biomass. Similarly, looking at the proportion of diatoms in the phytoplankton community, if the ammonium inhibition hypothesis is true, then we would expect a negative relationship between the proportion of diatoms in the community and ammonium. But if it's false, there might be a neutral relationship or even a positive relationship between diatoms and ammonium. To answer these questions, we use water quality data collected from 22 sites throughout the Delta, collected monthly from 2016 to 2023. This data comes both from our own USGS monitoring along with the Department of Water Resources EMP data. And we have sites in the North Delta represented here as triangles with the wastewater treatment plant up top, right below Freeport, which is at site FPT. And then we have South Delta sites, which are more influenced by the San Joaquin River, and West Delta sites that go out to Sassoon Bay. This is just an easier way to visualize where the sites are and what impacts they're having. We collected numerous water quality parameters, but I'm just going to focus on ammonium, nitrate, chlorophyll, and the proportion of the phytoplankton community that's made of diatoms for this talk. I use generalized additive models, also known as GAMs, to answer these research questions. For ammonium and nitrate, to explain variation in site concentrations, I used the effluent-derived concentration from the Sacramento wastewater treatment plant, which is the effluent concentration corrected for Sacramento River discharge. So it's at a relevant concentration for what is experienced in the Delta. And a big benefit of GAM models is that they can measure nonlinear relationships, which are represented here by the parameters in parentheses, preceded by an S for a spline. And given the nonlinear expectation for ammonium affecting phytoplankton, this is a good fit. And we also used months of the year, site, precipitation, and the proportion of flow in the Delta that goes out into the San Francisco Bay relative to the proportion of flow that's diverted for other uses as our covariates. We had the same model set up for nitrate in the Delta as well. We used a GAM model for the phytoplankton research question similarly, but in this case, we looked at ammonium, phosphate, and nitrate as covariates at the same time, along with site, month, and time as a continuous variable. And instead of just looking at the effluent concentration, we looked at the effluent plus Freeport concentration, which is the concentration of ammonium or nitrate directly below the wastewater treatment plant. So this is the inflow from the Sacramento River, essentially, that could be impacting concentrations in the Delta. And we chose to use this upstream source from the Sacramento River rather than the site concentration as a covariate because of the potential drawdown effects of chlorophyll. We wanted an upstream input that could be impacting things. So for our first research question, we need to figure out what the baseline is for how the wastewater treatment plant effluent is affecting water quality conditions in the Delta before we get to our other research questions. The plot on the left shows the ammonium GAM model. The x-axis has the observed range of effluent-derived ammonium concentrations, which are the effluent concentrations corrected for Sacramento River discharge. And I used a marginal effects package in R to visualize the GAM slope for each site. And significant relationships are shown as solid lines, and non-significant relationships are shown as dashed lines here. So just looking at the North Delta, we see that there are significant relationships for most of the sites that are downstream of the wastewater treatment plant, except for Freeport, which is upstream of the plant, which makes sense that that wouldn't be impacted by effluent. And the strength of the relationship tends to decline the farther downstream we get, which also makes sense. And there's roughly a 1-to-1 slope between effluent ammonium and site ammonium at our closest site, which is C3A. In comparison, for the South Delta, only the 3 northernmost sites had significant positive relationships. And in the West Delta, all of the sites had significant relationships, but the slopes were much lower in comparison to the North Delta. So if there are effects this far out, they're having less of an impact. In comparison, when we look at nitrate, we see a lot of non-significant relationships. So for the only significant relationship we saw was actually in the South Delta, which might have even been spurious. And a reason for this could be the low nitrate effluent concentrations prior to the upgrade, as we can see in the plot on the right here. However, following the upgrade in April 2021, shown by the dashed line, we see this increase in nitrate due to biological nutrient removal and greater nitrification rates that are converting a lot of the ammonium into nitrate. So it could be a reason that we'd expect post-upgrade relationships to differ. So now that we've established the baseline for how effluent was affecting nutrients in the delta pre-upgrade, what does it look like post-upgrade in our GAN models? In the case of ammonia, there's actually not enough variation for us to even run a model post-upgrade. Essentially, all of the ammonium and the effluent pre-upgrade has been converted into nitrate post-upgrade, and there's not enough variation for us to test the relationship anymore. However, when we look at nitrate, now there are several relationships we can see. So in this top row here is the pre-upgrade relationships that I already talked about, and the bottom row is the post-upgrade relationships. Now we see positive relationships between effluent nitrate at sites C3A and SDC at Walnut Grove post-upgrade that weren't there pre-upgrade. However, there aren't a lot of other positive relationships, so it seems like the effects of nitrate aren't going out as far downstream in the delta compared to ammonia. However, there are a couple of odd negative relationships in the south delta. One reason for this could be the amount of agriculture and agricultural islands, both within the delta itself and in the San Joaquin River. And while the effluent concentrations of nitrate have a negative relationship with discharge and precipitation due to dilution, increased discharge and precipitation can lead to higher runoff and more inputs of nitrate into the south delta. So this could be a case of a correlation rather than a direct effect. So we've seen that the wastewater treatment plant upgrade had big effects on nutrients in the delta, but what does this mean for phytoplankton? Do the phytoplankton even care that the nutrients have changed? Looking at our chlorophyll GAN results for ammonium first, the model's a little bit different in that I'm just showing all of the sites together, and I'm only showing the significant relationships. So it's not divided out into the north, south, or west delta anymore. But we see that the river plus effluent ammonium, or the effluent concentration of ammonium downstream of the wastewater treatment plant, tends to have a positive relationship with chlorophyll, which went against our expectations with the ammonium inhibition hypothesis. And looking at nitrate, there also were more positive relationships compared to negative relationships for ammonium and chlorophyll. So it seems that chlorophyll and phytoplankton biomass might benefit more than they're harmed by increased nitrogen, regardless of form. Then looking at our chlorophyll, or our diatoms that are making up the phytoplankton community and are part of the chlorophyll, we see that there's only positive significant relationships in this case, looking at the river plus effluent ammonium concentration. And when we look at nitrate, it's largely the same, where increased nitrogen, regardless of form, is leading to more diatoms in the phytoplankton community and less cyanobacteria. It's in another plot I don't have time to show here. So with all of that said, three things that I hope you can remember from this talk are that wastewater effluent can have far-reaching effects on water quality, even in a system as hydrologically complex as the delta. Second, upgrades to the wastewater treatment plant resulted in changes in effluent effects that can have far-reaching impacts. And lastly, the phytoplankton biomass and the proportion of diatoms in the community had positive relationships with nitrogen regardless of form. However, even though we saw these positive relationships, it's unlikely that increased nitrogen can counteract the historic decline in phytoplankton that we've seen. And looking at our model, it might only increase the chlorophyll by about 2 micrograms per liter. So not enough to have a huge impact. But some implications from this work are that it could be really important to continue to look into nutrients, given that heat waves and increased drought events might be more prevalent in the future, which could lead to dilution along with increased water demand, which could cause higher nutrient concentrations. There's also many wastewater treatment plant upgrades that are in the works, both within the Bay Delta region and also globally. And given that they can cost billions of dollars, these methods and results could be relevant for other researchers or managers interested in what kind of environmental impacts these upgrades might have environmentally. And with that, I would like to thank everyone who's helped with this project and answer any questions you have.
Okay, I think we have time for 1 or 2 questions.
Thank you for that. I was wondering if you could put the wastewater treatment plant in the context of other sources of nitrogen in the system, like benthic, diffusion and other urban runoff sources.
Yes. Yeah, so historically, pre-upgrade, the wastewater treatment plant was the largest ammonium source for the North Delta, at least, but obviously not post-upgrade. But because of the reduction in nitrogen overall and reduction in DIN, there are other sources of nutrients that are more important now, like agriculture. So agriculture is probably the biggest driver at this point for nutrients and especially nitrogen.
I was just curious, so the upgrades were specific to the ammonium, like that didn't affect anything else of the runoff? That was kind of like the only focus?
Sorry, can you say that again?
Sorry, was the ammonium fixing the only kind of outcome of the upgrades?
For reducing ammonium, they had other effects too in terms of, essentially all of the nutrients were reduced, like phosphorus was also reduced, given that there's biological nutrient removal and they're uptaking nutrients. I think there's other effects too for reducing pathogens, but Tim Musson would, have more details right away.
Thank you.
Okay, next we will be hearing from Ellen Preece, who is an environmental program manager with the Department of Water Resources. She will be speaking on spatial and temporal patterns of cyanobacterial harmful algal blooms in the Sacramento-San Joaquin Delta and the implications for monitoring.
Okay, now we're ready. Good afternoon. Today I'm going to be presenting the second of a two-part series of papers that was submitted to the San Francisco Estuary and Watershed Science, and they're currently under review. Both papers are exploring spatial variation in harmful algal blooms across the Delta. The first paper is looking at environmental drivers, so temperature, nutrients, etc. And then this paper that I'm going to present today is looking at what we're calling CHAB parameters, so different tools that you can measure harmful algal blooms with across the Delta. Both of these papers are a direct outcome of the CHAB monitoring strategy that my co-authors and I wrote and was published by the Delta Stewardship Council in late 2024. So the first part of the strategy was a data synthesis that informed the different management recommendations and goals in the latter part of the strategy. And since we wrote that strategy, we had the ability to dive into that data synthesis a little bit more, collect some additional data. And so that's what I'm going to be presenting today. So first, I just want to highlight that there are numerous challenges in monitoring cyanobacteria harmful algal blooms. in the Delta. We have this complex mosaic of different habitat types. We have areas like open channels, so the flowing rivers that have higher velocity. And then we have dead-end sloughs and marinas. These tend to have warmer temperatures and longer residence times. And then we have areas that are flooded islands and side channels that are kind of an intermediary between the two, so they have a more intermediate residence time, less velocity going through than the flowing rivers, but the tides are impacting these areas a bit more than the peripheral areas of the Delta. There's this strong spatial variability in hydrodynamics and residence time that I just mentioned. And then we have this very highly seasonal and interannual variability in our water year types, ranging from very wet years to drought years to multiple extended drought years. And all of these impact harmful algal bloom dynamics. And then uncoordinated monitoring programs with differing objectives and methods leads to this inconsistent collection of different data types, and therefore we have inconsistent metrics of harmful algal bloom data across these different data sets. So one of our goals of this paper was to take all of those disparate data sets and to synthesize them to evaluate the spatial variation in harmful algal blooms and to determine which regions of the Delta are most prone to harmful algal blooms, and also look at temporal patterns in the blooms. And the goal of this is to inform future monitoring strategies in coordination with that part 1 paper that I mentioned. And so this is the map that we used in our paper. And we have the Delta split into 8 different regions, and they're color coded. So each one of these dots represents some data that we got. So we have at least one of our data sets come from these individual dots. So down in the south, we have what we call the South Delta region, which is that green color. The light green color is the Central Delta. The dark purple is the Upper San Joaquin River. The pink is the Lower San Joaquin River. Yellow is East Delta. Light blue is Lower Sacramento River. The slightly darker blue is the Upper Sacramento River, which you can see has very limited data. And then the dark blue is the Cache Slough Complex. And then there are some diamonds on here. We have the diamonds for Discovery Bay are green, purple are Stockton, and pink are Big Break. And these are known harmful algal bloom hotspots. So for the methods, we summarized data from 2014 to 2022, and we analyzed chlorophyll A, microcystis as measured by microscopy, microcystis as measured by qPCR, microcystin concentrations, and then we looked at the microcystis visual index scores. The data was collected from both routine monitoring programs as well as special studies. And I just wanted to note that we did consider remote sensing, but it's not addressed further in this talk. So now I'm going to dive into the results. The first is chlorophyll A. So we had 6 regions that we had enough data to analyze for this analysis. And the takeaway here is that the highest summertime chlorophyll A concentrations occur in the South Delta, followed by the Upper Sacramento San Joaquin River. But I just wanted to point out a couple things about chlorophyll I think that many of you in this room know about, which is first, we have that picture of Stockton on the top here, and that was May 2025. Stockton has pretty high chlorophyll concentrations, but it's not always because of cyanobacteria. And this is a perfect example. You can see the chlorophyll in this particular picture is driven by diatoms. And then I also wanted to highlight the lower picture is in Turner Cut, and I would say this is about the worst that I've ever seen microcystis occur in that area. And when you take a bottle and you're scooping that water, it's hard to collect those microcystis colonies. And so the chlorophyll that you are getting may not actually be reflective of the cyanobacteria that are present. Moving on to microscopy, we had a fairly small data set for this, and we didn't have any significant differences across the regions, but in this particular box plot, the Lower San Joaquin River and Central Delta tended to have a bit more microcystis. Next, discussing the Microcystis Visual Index. And so many of you may be familiar with this scoring system. We have 1 through 5. 1 is when microcystis is absent, and 5 is when you have very high concentrations. And this is taken by people looking over the side of the boat or collecting a bucket of water, and then they are recording a subjective score of 1 through 5. So on our plot here, we were looking at the frequency of occurrence of these different numbers, 1 through 5. And so yellow is the 1. That means that microcystis was absent in these different regions during that period. And then the dark purpley color is the highest, so the most severe amount of microcystis that you may see. And the takeaway from this figure is that most of the microcystis, according to the Microcystis Visual Index that we see in the Delta, is from June to October or November. In some regions, we may see some microcystis be present as early in April and May, but it's really those summer and early fall months that we're seeing microcystis in the water column. And really, you can see that the bars are highest in that July through September period, which is when we seem to see the most severe blooms. Okay, now moving on to total microcystis gene copies per mil. So this is microcystis as measured by qPCR, and we had data from 2014 to 2019, and then also 2021. And we were able to add Stockton and Discovery Bay, 2 of our hotspots, into the 2021 analysis. So each of these tiles, well, first of all, we took all of the data and we split it into 4 categories ranging from low, medium, high, and very high. So this is all based on the available data that we've made those classifications. And then the gray tiles would be non-detect. So each of these tiles represents the maximum concentration that was measured on in a particular month at a particular site. But we have little dots that show all of the different samples that were available for that region and month. And so you can see that there is some variability in the qPCR samples across month and across the different sites. But overall, microcystis was highest in 2014, 2016, and 2021, all of which were drought years. And generally, it was lowest in 2017 and 19, which were 2 wettest years in the data set. And microcystis was highest in those dead-end channels of Discovery Bay and Stockton, which you can see on this figure in 2021 were all in the very high category. They at least had 1 measurement that was in the very high category. Now moving on to microcystins. So for this analysis, we were able to compile almost 1,800 data points between 2014 and 2022. And 43% or 775 of those grab samples had detectable microcystins. The way the categories are for this figure is the light gray is non-detect. The very low is below the California caution threshold of 0.8 micrograms per liter. The yellow is any sample that falls in that caution threshold, so 0.8 to just below 6. Orange is the warning, which is 6 micrograms per liter, up to 20, and then high is the 20 micrograms per liter microcystin. So something to note on this slide is that only 24 of the detections, which equaled 1% of our data set, occurred between December and May. So the toxins are really primarily occurring from June to November. And of those 24 detections, most of those were in Big Break, a few were in the Stockton area, but it was actually like several data points from a single day. Only Big Break, Discovery Bay, Stockton, and occasionally the upper San Joaquin River have exceeded the California danger trigger. And in open water bodies where flakes are more dispersed and they are less likely to form the scums, microcystis do not dominate as much. The microcystins are generally below the warning trigger and more frequently below the caution. So this is the same data, just looking at it slightly different. These are ridgeline plots. And then on the far right are a plot showing the percent of non-detects. So a few things to take away from this figure is that Stockton, Discovery Bay, and Big Break, once again, have the highest toxin concentrations. It is worth noting that Stockton and Discovery Bay in particular, a lot of the samples are response data, so a bloom's been called in. And so that could be one reason that we are not seeing very low concentrations at those sites. Another takeaway is that the Upper Sacramento River, 100% non-detects. And then the East Delta, we had 2 detections there, but the majority of the samples there also non-detect. And the Upper San Joaquin River, Central Delta and South Delta has significantly higher microcystins than East Delta cash slough in both the lower and upper Sacramento River. Okay, so this was somewhat difficult because we had the disparate data sets. We only had some regions for some categories, but we wanted to take it all and look at it all together and see if we could look at some patterns. And so we came up with this heat map, and the region is on the x-axis, and then on the y-axis we have chlorophyll, then CPCB, so that's microcystis as measured by qPCR. MC stands for microcystin, micro is microscopy, and then MVI is the microcystis visual index. And we have the median, and basically the warmer or the redder the color, the higher one of those categories were. We did some statistics before we put together this figure, and we found that we should include July through October in this figure. The other months fell out of the figure. And so some takeaways from this figure is that South Delta and Stockton, so these are all the regions, and then I was able to add Stockton into this too, show the strongest harmful algal bloom indicators across multiple parameters. The microcystins remain relatively low across most regions, except for those dead-end channels or dead-end sloughs. And the cash slough complex, East Delta, and Lower Sacramento River have less issues with harmful algal blooms than the Central Delta, South Delta, and Upper San Joaquin River. So I just wanted to go through a few of the conclusions from the paper. So we have some spatial and temporal considerations for future monitoring. First is to expand monitoring in harmful algal bloom hotspots. There's no routine monitoring in these hotspots. There's also probably hotspots that haven't been identified. So future work could identify those sites. Next is broadening the habitat coverage. So suggest including more monitoring in flooded islands and side channels. We found that the East Delta was lacking a lot of monitoring, and in our first paper, we also found that that was one of the regions that was warming faster. It also than the other regions, and so it may be more prone to harmful algal blooms in the future. And then there's a number of marinas and dead-end sloughs in that region that may be prone to blooms. And then we also suggested focusing the monitoring window to June to October or so, especially July to September when harmful algal blooms and toxins peak. Something else that we included in the paper was looking at monitoring and research tools, and we set up our discussion around this integrated framework that Summer and others has published. And we discuss how effective harmful algal bloom monitoring in the Delta requires 4 components, which is routine monitoring, targeted research, modeling, and tool development. And some examples of tool development is standardizing solid phase absorption toxin tracking deployment. So these are passive toxin samplers that can be deployed for a week or 2 weeks period of time. And so we're saying you can standardize the duration that you're measuring and the toxins that you're measuring for. Expand Sentinel-2 remote sensing applications to detect bloom hotspots, since most of the Delta is not currently monitored with remote sensing due to the small channels. And then a targeted research example is evaluating how microcystis visual index rankings correspond to bloom magnitude and toxicity. And there is some work moving forward on that separately. And then modeling an idea would be modeling how blooms in some growing regions may influence adjacent advective regions. And then in the paper, we have a table of examples of how to integrate multiple methods into HAB monitoring and research. And this is just one row of that table. But we have a variety of different monitoring tools that we identify and then explain the type of information that it provides, pros and cons of that particular tool, and then how that tool could be used to support management, as well as how it could be used to support mitigation. So to conclude, the harmful algal bloom risk varies across the Delta. The highest occurrences are in the upper San Joaquin River, Central Delta, and South Delta. Lowest occurrences in the lower Sacramento River and Cache Slough complex. Monitoring can be more strategic with that focus on the period when blooms are most severe. And climatic changes will likely increase harmful algal bloom risk. So increased droughts are expected to exacerbate blooms, and increasing pressure on freshwater resources at the same time may further influence harmful algal bloom dynamics. And we just identify this need to develop adaptive strategies to address HAB risk. And then this project couldn't have been done without all the people that helped review the harmful algal bloom monitoring strategy. And we're grateful to all the individuals who helped to the writing and review of the strategy, as well as everyone that shared the data to make this synthesis possible. And just thanking everyone, many of you are in the room for helping read and provide input. And then I just wanted to conclude with, this is one of the oldest photos that I have in my photo library from a former colleague. This is the Stockton Channel Turning Basin in July 2012. So thank you.
Okay, we have time for one question. If anyone has a question.
Thanks, Ellen. That was a really nice talk. So you noted some instances, like I think at Big Break during 1 year, you detected microcystin concentrations above the danger level, I think, and that was in October. So your recommendation is to monitor during June to October, but I'm wondering with climate change, do you think that we could start seeing concentrations that exceed some of those CCHAB recreational advisory levels going later in the year, like into November?
November is definitely possible. And I guess, especially during a drought year, I guess maybe I should have specified that. I think during drought years, extending the monitoring later is probably a good idea.
Thanks.
Thank you.
Thank you, Ellen. Okay, next we will be hearing from Alice Tung, who is a PhD candidate at the UC Davis Center for Watershed Sciences in the John Durand Lab. Her research focuses on water quality and primary productivity in seasonally managed wetlands within the San Francisco estuary. And she will be completing her dissertation and submitting it at the end of this week. Alice will be speaking on elevated phytoplankton production in seasonally managed wetlands. And also this presentation will not be recorded, so make sure you take good notes. With the USGS California Water Science Center. He works with phytoplankton modeling and aquatic biogeochemistry, and he will be speaking on the assessing drivers of phytoplankton blooms in the South Delta.
Hi, thanks everybody for being here. Today I'm going to talk about our work in the South Delta assessing drivers of phytoplankton blooms. So just as an introduction to the South Delta, it has a different spatial extent in every study, but for the purposes of our study, it encompasses the region inside this box. So it goes from San Joaquin River to the east, all the way to Clifton Court Forebay in the west, and up to Old and Middle River Corridor to the north. So most of the past work here is focused on salinity and dissolved oxygen with relation to state water project exports, not necessarily phytoplankton. So a lot of this data has not been fully analyzed yet. So that was exciting for this project. It's obviously important when you have the water project infrastructure nearby, so maintaining water quality for water exports is important. So this is a strategically important region. Also, the high nutrient concentrations from the incoming San Joaquin River, as well as the warm temperatures. A lot of these channels are small, narrow, shallow distributary channels, so they heat up very easily. So both those high nutrients and warm temperatures make this a concern for harmful algal blooms that can degrade water quality. And this region was already brought up in Ellen's talk as, having high potential for cyanobacteria, harmful algal blooms. So just some more background on the complex hydrodynamics that make this region unique is that exports have a very high impact on the flows. So we also have temporary barriers placed every May through November, which are delineated by these yellow boxes. And so those are riprap barriers placed that prevent or that maintain water levels upstream for irrigation in this region. So we also have those in place, which make it even more complex. But during periods where we have low San Joaquin River inflows and high exports, that when the export flows exceed head of old river flows here, that's when we can get these reverse flows that pull water towards the pumps instead of them flowing out naturally towards the Bay Delta. And we also have some weird null zones happening where we have opposing flows, reverse flows and seaward flows meeting. So it can be quite complex hydrodynamically. So the reason I talk about hydrodynamics is because it can have strong controls on phytoplankton community composition and abundance. So I have two scenarios shown here. The one on the left is a high mixing strength scenario where we have short residence times, a lot of water speed, and a lot of turbulent mixing. And so this creates a variable light environment that can favor small cells with fast growth rates, such as diatoms. These small cells don't have to worry about settling out in the water column into the sediment because they're constantly entrained by these flows. And they also, with their fast growth rates, can take advantage of short residence times and still accumulate in high enough biomasses to cause a bloom. On the scenario on the right, we have a lower flow and lower mixing strength scenario, and that can favor, that can create a more consistent light environment where cells with motility and buoyancy regulating adaptations can dominate. Because of the lower mixing strength, they're able to take advantage of those adaptations and reach areas with more light availability. They also favor taxa with slower growth rates, so they may take longer to accumulate, but once they do establish a population, they can then outcompete other organisms for light. And also we see organisms with colonial morphology. It prevents them from settling out as fast in the water column due to less mixing strength and training them to the surface. So with that in mind, we used a lot of different agencies' data there's a lot of data collection in the South Delta, luckily. First and foremost, the Department of Water Resources North Central Regional Office maintained most of the stations in our region. We also took data from EMP, Operations and Maintenance, and DICE. We also used Bureau of Reclamation data, as well as our own USGS data. The main parameters that we focused on for continuous parameters was chlorophyll A, turbidity, water temperature, and water velocity. And we also used a host of discrete parameters. The period of record for most of these parameters ranged from the year 2000 to 2023, so quite a long period, but this varied quite a bit because not every parameter was measured continuously for this whole 23-year segment. So it was quite complex dealing with the different period of records. But we tried to analyze as much data as we could get our hands on. So the study objectives were to characterize phytoplankton communities in the South Delta and assess the prevalence and potential impacts of cyanobacterial harmful algal blooms. We didn't know if they were a potential threat to this region or if they were common occurrences. We also wanted to identify drivers of blooms because even if blooms are not harmful, they're still important for fueling the food web. So we want to know what drivers control blooms, as well as blooms of harmful taxa. So we started with bottom-up controls on phytoplankton, which are nutrients and water temperature in this case. So the plots, we show dissolved phosphate and dissolved inorganic nitrogen, which are the main forms of nutrients that phytoplankton can utilize. And the red lines, the red dotted lines represent the concentrations at which these nutrients can become potentially limiting for growth. So we're well above this. These plots are on the log scale. We're well above the limitation concentrations for these nutrients. So nutrients were generally replete in this region. Again, we're getting a lot of agricultural runoff from the San Joaquin River. We also saw very warm water temperatures. So this dotted red line for water temperature is Peggy Lehman's 19 degrees Celsius value from our 2013 paper. So above that temperature, that's where we can see microcystis dominate and blooms form. So for most of the summer growing season, we're above that 19 degrees Celsius threshold. So both high nutrients and high water temperatures set up translate to high growth potential for primary production. So looking at the actual phytoplankton biomass data, which was discrete chlorophyll A, here we have it plotted out for each distinct water body in the South Delta. And we see a lot of concentrations above 60 micrograms per liter. We can get some pretty large blooms in this region. We considered blooms to be anything above 16 micrograms per liter. This corresponded to the 82nd percentile of all of our chlorophyll A data in this region. And it also is the midpoint in the World Health Organization bloom threshold. So we saw that blooms can be quite high, up to 60 micrograms per liter, but the baseline conditions is most of the time chlorophyll A is below 10 micrograms per liter. And then we also wanted to focus on microcystis because it's the sole confirmed microcystin producer in the Delta, which is a harmful cyanotoxin. So we looked at microcystis visual index scores, which again is a semi-quantitative measure that you make by looking at the water. 1 being microcystis is absent, 5 being that there's surface scums. So we saw that surface scums, or values of 5, were relatively rare. So this plot is just showing the proportion of each microcystis visual index score at each of our regions in the South Delta, and it's plotted by water year type. Because we only included 2019 to 2023 data in this, we might have some sampling bias because we only had 2 critical years and 1 dry year. But in our data, we see that microcystis was more common during dry years. It was present at higher abundances with some of these values of 5 corresponding to surface scums. But we would expect critical years also to be bad for have higher microcystis biomasses because water temperatures are generally warmer, flows are lower. So microcystis is present, but it's not necessarily causing a lot of occurrences of surface scums. Diving deeper into the community composition of all taxa, we looked at phytoplankton enumeration data at each of the sites. So these regions are presented from most upstream in the San Joaquin River to the most downstream adjacent to Clifton Court Forebay Inlet. We can see that there is a distinct shift from diatoms in the more upstream turbulent stations. Again, this station has higher flow and mixing strength than these further downstream stations near Clifton Court that transition to more freshwater tidal influences on flow. And as we go from these high turbulent stations from more diatom dominated, we do get more of these potentially toxigenic cyanobacteria taxa that are shown in the red. So periodically, these toxigenic taxa are making up the largest portion of the biovolume and dominating the community. However, I want to caveat this, that whenever they dominated the community, the chlorophyll A biomass levels were below our 16 microgram bloom threshold. So these were not documented harmful algal blooms. So while toxigenic taxa are present, they're not necessarily forming harmful algal blooms, which is an interesting finding. The biggest impacts that cyanobacteria had on water quality were with taste and odor compounds. So there's an 8 nanogram per liter threshold for both geosmin and MIB, which are both compounds that can cause aesthetic issues with drinking water that affect the taste and odor. And we exceeded that threshold in 14% of our geosmin samples and 9% of MIB samples. We did detect microcystins. They were the only cyanotoxin detected. and they were detected in 12% of samples, but the highest concentration was only 3.87 micrograms per liter, which is lower than the 6 microgram per liter caution or warning threshold, but above that 0.8 microgram per liter caution threshold. So we wanted to identify drivers of microcystis blooms. Even though they weren't prevalent at very high biomasses, we wanted to figure out what might be controlling them for future scenarios where they might become more common. So we ran some Bayesian ordinal regressions on the microcystis visual index scores, and we ended up binning the scores to create larger differences between each of the categories, to hopefully create some more meaningful differences between the categories and make the analysis a bit more robust. We found that water temperature and prior week water speed, so this prior week water speed was the water speed the week prior to each microcystis visual index score, and that's a time scale that we think is more relevant to the growth of microcystis or blooms forming. We found that with water temperature as it increased, the probability of microcystis being absent steadily decreased. And we found a threshold at 22 degrees Celsius above which the probability of detecting microcystis at low abundances was greater or equal to 50%. So it was interesting to see, that reflected in the data that the warmer the water temperatures, the more likely you are to have microcystis present. And then with prior week water speed, we found that the faster the water speeds, the higher the probability of microcystis being absent. Again, it's a buoyant taxa, so it prefers less water speed, less turbulence, so that it can use its adaptations with buoyancy regulation to reach the surface. So at water speeds below 0.18 meters per second, we saw the probability of detecting microcystis at low abundances was greater than equal to 50%. Because we didn't necessarily see large problems with microcystis in the data, we wanted to predict what might cause chlorophyll A blooms, because even beneficial blooms of diatoms, for instance, matter for food webs. So we assessed drivers of chlorophyll A exceedances of 16 micrograms per liter. So we trained a random forest model on our data to predict exceedances of that 16 microgram per liter bloom threshold. We tested the model against a holdout data set, and it had an accuracy of 92%. And we found this is a plot of SHAP values. So each point represents an individual data point in our data set, and the location to the left or right of 0 signifies anything positive corresponded to that data point contributing to favoring model prediction of a bloom occurring. The more positive values, the more influential that data point was on a prediction of bloom. And to the left, we see data points that favored model predictions of bloom not occurring. And then the actual value of each parameter is shown with warmer colors indicating higher values. So say for water temperature, the warmer colors indicate warmer water temperatures. So we can assess the directionality of these relationships as well. So we found prior week turbidity, San Joaquin River flow region, and prior week water temperature to be the strongest drivers of chlorophyll blooms in the South Delta. However, I want to caveat that the turbidity relationship upon further investigation seemed to be a spurious correlation, where when you reach bloom concentrations high enough, the phytoplankton themselves can actually induce a turbidity signal in your instruments. And we found this with a number of different other references. So we suspect that with higher turbidity, we don't actually see a higher probability of a bloom. It's just detecting the bloom itself. But the main one we want to focus on is San Joaquin River flows. So the lower San Joaquin River flows, the higher the bloom probability. And we'll dive into that further. So here we see San Joaquin River flows plotted on the x-axis. So with increasing San Joaquin River flows, we're getting decreasing SHAP values, which mean that those data points favor blooms not happening. But anything above this 0 line, all these data points above the 0 line favor a model prediction of blooms occurring. So here we can see that there's a threshold at about 125 cubic meters per second, below which those flow levels actually favor a bloom occurring, and paired with high water temperatures. So this is telling us that during the summertime, when we have low San Joaquin River inflows, we're more likely to see chlorophyll exceed that 16 microgram per liter bloom threshold. But this threshold did differ by region. Each region is hydrodynamically unique, and so there's different thresholds below which San Joaquin River flows would favor blooms. So in conclusion, despite warmer water temperatures and high nutrient concentrations, we did not find that harmful algal blooms were a common occurrence in the South Delta. They were somewhat rare. We did find that gradients of water velocity and turbulence likely drive variation in phytoplankton communities, with these upstream riverine stations in the San Joaquin River being more dominated by small-celled diatoms that are more adapted to those turbulent conditions. And then further downstream near Clifton Court Forebay, with less mixing strength, we saw a more colonial cyanobacteria. We also found that prior week water speed and water temperature were important predictors of microcystis abundance, with warmer temperatures and lower water speeds favoring higher microcystis abundance. And then we found that San Joaquin river flows, region, and prior week water temperature were important predictors of chlorophyll A blooms, with lower San Joaquin river flows and warmer temperatures favoring chlorophyll A blooms. And the reason that this all matters is that because there's likely going to be altered flow regimes in the future due to different management actions and climate change impacts on precipitation in the region. So understanding how hydrodynamics and flow can influence the occurrence of harmful algal blooms in this region is important to maintain water exports for the state and federal water projects. So with that, I'd like to acknowledge the California Department of Water Resources for funding this research. Special thanks to Brooke Rosenau and Jared Francic at the DWR and CRO for providing domain knowledge on this complex area of the Delta, as well as various modelers in DWR for providing helpful input and data. So thank you.
Okay, we have time for one question. If there's no questions, then we'll go ahead and move on to the next speaker. Thank you. All right, next we will be hearing from Keith Bouma-Gregson, who is a research biologist at the United States Geological Survey. And Keith will be speaking on designs for cyanobacterial harmful algal bloom monitoring in the Sacramento-San Joaquin Delta.
So you've heard the joke about the why the pony couldn't sing because it was a little hoarse. So am I. So apologies about my voice coming off of a cold, but I'm also excited to be here. So my name is Keith Bouma-Gregson. Sorry. And I'm at the USGS and talking about cyanobacterial harmful algal bloom monitoring. So I'm at the biogeochemistry group at the California Water Science Center. Our funding comes from multiple different entities for our different projects. This project was funded by the State Water Board, Division of Water Rights, but I want to also acknowledge and thank all the different funding groups that have supported our different work over the years. So taking a quick step back into thinking about HABs in the Delta, the first report of a bloom was in 1999. And since then, there's been a lot of research that's done, primarily focused on microcystis and toxic microcystin. And this has been through, mainly through special research studies. And this has been pretty productive. There's been almost 30 CHAB specific publications or reports in that time period, but there's been no dedicated long-term monitoring program focused on HABs. This started to change in 2024 with the release of the CHABs monitoring strategy, which Preece was the lead author on, and you heard a little bit about that from her. And in this strategy, it laid out 5 goals for what they could be pursued to try and improve the situation around CHABs data collection and collaboration in the Delta. And goal number 3 was to develop a CHAB monitoring program. And the State Water Board's Division of Water Rights has been trying to support various projects that would help implement the different goals in the strategy. And so they approached the USGS to try to move forward Objective 3.2, which was identifying priority monitoring parameters, locations, and sampling periods to start to build and think about what a HAB monitoring program could look like. And so in conversations with the water boards, we kind of landed on this notion of creating a designs report. And this figure here at the bottom kind of shows how we thought about that. So we thought of the strategy as being the higher level vision of where we're going. Like this is our targeted objectives, but it doesn't necessarily get into the details of how we get there. And so that's the next step of what we saw this designs report is helping to fill, which is more of that map of if you want a monitoring program, here's the steps and here's more of the details that you would need in order to actually like get that monitoring program. However, we then did draw an additional boundary on our scope where we weren't going to be so detailed that you could actually like hand an operating procedure to a technician or a staff person. So we still see that there's an additional step of taking the content of the designs and other documents and then finally coming together to actually write out a program plan that would ultimately execute an actual monitoring program. So in this designs report, the goal of the report is to help agencies and stakeholders move from high-level recommendations to practical, actionable CHABS monitoring designs that are tailored to the Delta's physical, anthropogenic, and ecological landscape. In the report, you'll find information that provides background on the monitoring and modeling approaches, overview of current monitoring programs, guidance for selecting monitoring locations, indicators, and sampling frequencies, and then example designs to guide program planning. And the report is currently available. It was published as a preprint on the ESS Open Archive in December. And right now it's in the USGS publishing office, going through the final publishing aesthetics and things of the report. But you can access all the technical and scientific content now currently, and then within the next few months, we'll kind of have the like official USGS formatted version. But as I said, the technical content is not changing through that formatting process. So the approach that we undertook was we did a lot of extensive literature review of Delta publications, as well as other CHAB monitoring research. We conducted many informational interviews and conversations with Delta scientists and other staff and scientists from other systems. We assessed data from the Delta to try to understand the specifics of how we could tailor the design ideas to meet the dynamics of the Delta. And then we used management questions to inform design decisions. So this here is a list of some of the folks who helped provide technical input and review on this report. And a big thanks to any of them if they're here in the room. So this figure is one of the overarching key figures from the report. And the report primarily focused on routine CHAB monitoring, very much akin to the different IEP programs. But we did want to communicate that this is effectively not enough to meet every single management need. And the other key takeaway here in this figure is at the bottom, our monitoring goal for the data we're trying to collect is to answer CHAB management questions. And in order to do that, we have to rely on all different sorts of data types and different programs or projects. And this kind of pretty much like echoes and aligns with one of Ellen's concluding slides, which is that we still will need to dedicate resources to research special studies, event response, data management, data integration. And that the routine CHAB monitoring can't do it all. So when you're sitting down to think about how to build out a monitoring program, one of the questions that's at the forefront of your mind is how do you monitor effectively yet remain affordable? We'd all like to measure every parameter everywhere all at once, but there's just not enough time or money to do that. So we had a couple guiding principles that we use to help prioritize how the design decisions that we might make. So one is to make sure we always had a clear purpose for where, when, what, and how we were monitoring. We also use the philosophy of tiered monitoring approaches to scale the monitoring effort according to the CHAB risk level, and also to coordinate and leverage with other programs to optimize staff and financial resources. So as we continue to go down this path of making sure we had clear purposes for why we were doing things, it became apparent that we couldn't do everything in one design. And so the report effectively concludes with 3 different designs for 3 different purposes. One is looking at environmental drivers. One is ambient status and trends, so kind of looking at the representative conditions across the Delta. And one is focused on public health impacts and risks. The largest section of the report is called Design Considerations for the Delta. And in this section, what we did is we broke the delta into several regions, and for each region, we reviewed the hydrodynamics and environmental conditions. We reviewed the data available to assess the CHAB status and severity in that region, and then identified different monitoring gaps that might currently exist. We also looked at, have other sections looking at specific monitoring methods and which types of methods might be most appropriate in the Delta. And we also have a section on food web monitoring as well. And so as an example of the type of content that's in this section is this figure here is from the report, and it shows a map of old and middle river corridors. And what we've done is highlighted the continuous stations or the places where data is collected, where there's in situ chlorophyll sensors or discrete chlorophyll samples as part of other monitoring programs. And then this panel here shows some of the boat-based high-resolution mapping data that our group has collected over the years. And so this is where we have a flow-through system on our boat and are able to pump water through the sensors, collecting high spatial resolution data. And what you can see is that in the top two panels, July of 2021 and 2022, there was a bloom in Frank's Tract with elevated chlorophyll. And that chlorophyll starts to move into Old River and get drawn southward towards the pumps. And then in 2023, there was no bloom, but there was still some elevated chlorophyll in Old and Middle River. So this is an important transport pathway for potentially blooms in the Central Delta. And when we look at the monitoring stations, so D28A and OBI, this is part of the environmental monitoring program. From this station down to the Clifton Court Forebay Inlet stations, there's only a station at OH4, and this OH4 station isn't that comprehensive. Only discrete chlorophyll is collected there. There's no in situ sensor, there's no phytoplankton enumeration data. So in the report, we highlight that enhancements to that OH4 station to add continuous data, to add more phytoplankton community composition data could fill an important data gap as we're trying to understand what's happening to water as it's moving down Old River towards the export facilities. So after some lengthy discussion and interrogation of these different regions of the Delta, we try to then synthesize and stitch that information together into some actual potential designs. So the first design is an environmental driver's design, and the purpose of this is to have the data to understand what might be driving these blooms. And one of the conclusions in this section was that there's a lot of environmental data collected in the Delta. I was a little bit surprised and pleasantly surprised, I suppose, to sort of like generate maps like this showing every single in situ sensing station. And so one of the key gaps is really not so much that we don't have like enough temperature data in the Delta, but more that we're really missing the CHABS response variables, so toxin data or phytoplankton community data. Additionally, the antecedent conditions are really crucial for understanding the CHABS drivers. So whereas when we're thinking about some of the other designs focused on the CHABS response parameters, which use that tiered framework, we can't really use tiered framework when we're thinking about drivers because we really need to make sure we have all the nutrient data preceding a bloom. So in conclusion, this environmental drivers design actually has some of the fewest enhancements of the other two designs, partly because we have such a robust network of physical measurements in the Delta, and that more of the emphasis winds up being on collecting the targeted CHAB response variables so that we can then compare those variables to the physical data. So the ambient monitoring sorry, that threw me off. Yeah, the ambient monitoring design. This is kind of the main design of the report. And the goal here was to look at ambient status and trends of CHAB. So we're trying to get like the general data that could give us a general representative understanding of what the conditions are like in the Delta over time. And so we tried to leverage existing stations when possible. And fortunately, in the last few years, a number of stations have come online in some of the hotspot areas. So through Preece's work, there's now a station at Stockton, for example, that didn't previously exist there. We also, in the design, incorporated some of the draft stations or some of the proposed stations in the Bay Delta Plan draft, which is also proposing locations that previously hadn't been monitored, such as Mildred Island as well. And so when considering some of these new additions in the last few years, one of the last remaining gaps is really in the report is Discovery Bay. That's still not a part of any longer term monitoring program or plan, even though it does still continue to have bloom events. And then within the monitoring, within those stations, there's a design of like a tiered framework for how to collect samples. So it rests on tiered monitoring and visual indices. So visual indices are very commonly recommended within the HABs monitoring literature. This figure here on the left is from the World Health Organization and their guidelines, where they have 2 different alert levels, each with different visual indices. As you heard already, in the Delta, we have the Microcystis Visual Index, which, although not perfect, does give us a nice foundation to build upon. So in this ambient monitoring design, we have level 1, which is basically our routine monitoring that's happening year-round in a monthly time step. In this case, the key parameters are collecting discrete chlorophyll A and in situ chlorophyll fluorescence for your phytoplankton biomass. And then we're using the visual index as the very low cost and rapid method to determine if that chlorophyll might be generated by cyanobacteria or other taxa. And so you basically do that year round. The design also rests heavily on the notion of explicitly incorporating remote sensing data. We can get really broad spatial coverage using the remote sensing data, and that can be, again, a helpful baseline data set that provides high spatial and temporal coverage of the delta. Then as the potential for cyanobacteria to increase, that would trigger your level 2, where you now think you have elevated cyanobacteria. This can be triggered by a higher visual index value, or paired, you could have like a chlorophyll threshold or remote sensing threshold that could then be confirmed upon a visual index when you actually do the site visit. And then this level 2 focuses on microcystis and microcystins, because upon reviewing the data, that is really the only toxin that we really see high concentrations of in the delta. While other toxins have been detected, their concentrations are quite low. And so the report suggests using an adaptive management framework, where at this point, the greatest risks based on the data seem to be related to microcystis and microcystins. But if a new taxa were to come into the delta, or new toxins were to be detected at high concentrations, we should then go back and adaptively revise these types of designs to account for the changing conditions. So now if you get the level, if you suspect the higher cyanobacterial biomass, you collect additional samples. In this case, we're using qPCR and molecular methods as ways to quantitatively estimate the abundance of toxigenic microcystis in the system. At level 2, you would also increase the frequency from monthly to biweekly. And then level 3 would be where you would actually measure microcystin concentrations. So if you have a high enough qPCR gene count of your toxigenic microcystis, that would be the evidence you would use to suggest that you might actually have like elevated toxin concentrations, and then you would measure your toxin concentrations. So again, kind of the philosophy here is you're scaling your level of effort with the risk of cyanotoxin concentration. Some of the data that was used to draw upon from this design, this here is showing microcystis visual index values along the x-axis. Within the y-axis is toxin concentrations, and you can see that as you move to the higher microcystis visual index values, the toxin concentrations increase, and the statistical probability of exceeding certain thresholds also increases. And then for the qPCR data, this is the qPCR genes here on the x-axis. So this is the microcystin synthetase gene, and then the microcystin concentration on the y-axis. And again, as you get more and more of those toxigenic genes in your sample, the microcystin concentrations increase. And then you can use different probabilistic frameworks to identify statistically the particular thresholds that you might want to use to trigger different monitoring levels. And then the last design is focused on public health monitoring. So rather than looking at these broad, longer-term average conditions in the Delta, this is looking for more rapid risk assessment for contact and non-contact recreation. So here, the emphasis is on monitoring sites with high recreational use or with a history of elevated cyanotoxin concentrations, such as Stockton Waterfront or Discovery Bay. And then we also drew this large polygon around Old and Middle River, where we see elevated cyanotoxins and cyanobacteria, and there's also a higher amount of wakeboarding and water skiing in this area. And then in this case, the sampling methods use the statewide FHAB programs sampling guidance, which is looking at more targeting scum samples and worst case scenarios rather than average condition. So there's also a section of the report that focuses on the research and data gaps to achieve these designs. So while we're able to draw a lot on the data that's been collected, and Ellen also showed how much has been done in the last like 5 to 10 years compared to the previous 10 years, it's really astounding. But there's still some gaps that are there. So we have 9 special studies recommended, and these complement the 19 studies in the strategy. Some of these have a little bit of overlap, and we did that intentionally to underscore the importance of these studies and their need for the HABs monitoring. So this focuses on the visual indices, assessing the performance of our chlorophyll sensors, improving the relationship between qPCR and toxin concentrations, continued studies to assess the production of other cyanotoxins beyond microcystin, field validation of remote sensing algorithms, developing remote sensing indicators for monitoring and management, field sampling protocols for detecting colonies, assessing the impact of grazing by corbicula and other bivalves, especially now with golden mussels in the system, and assessing cyanotoxin thresholds protective of aquatic organisms in the Delta. And so in conclusion, some of the key takeaways are that we need these clear purposes for where, when, what, and how we're monitoring. What's primarily missing in the Delta are the CHAB response variables and monitoring locations prone to CHABs. Routine CHAB monitoring is not enough to address all the management questions, needs, and actions. We still need to think of this in a very integrated and holistic framework. The tiered monitoring is effective for scaling our resources with CHAB risk. However, it's often insufficient for collecting data on environmental drivers. And we still do have some conceptual and methodological research data gaps that remain to be filled. So with that, thank you. Again, here's the URL and the citation for the report. And welcome to take any questions now or follow up with me at the break or online. Thank you.
We have time for one question.
Thanks, Keith. So I totally understand the rationale for the tiered monitoring. I've done it myself, but you also mentioned we're missing the response variables. And if you're doing trend analysis, that gold standard would be the toxin concentration. So any mention in your work of recommendations for what would you do with the qPCR data if it was low enough, you didn't have a toxin concentration analysis, but then if you're trying to do a trend on your toxin analyses, that appears as oh, I never measured it. So do you have thresholds or?
Yeah, so I think in doing an analysis like this is going to require something maybe a little bit integrative across things. But this slide here, sort of the idea would be that you're sort of have to make an assumption that if your visual index is a 0, that your toxin concentration would be a 0 as well. And I think that's a pretty robust assumption to make based on now like a decade's worth of data. So the vision we would have is we would always have like a continuous time series of visual indices, chlorophyll, and remote sensing. And if you're in this zone here, you would sort of be assuming that even if you did have qPCR data, it would be a 0. And you kind of have to develop your statistical frameworks around that. So this would be kind of your baseline continuous, and then you would be having your qPCR and toxin concentration data only triggered when you have these higher concentrations. So like your long-term analyses could be done on remote sensing, visual index, and chlorophyll, and then your toxin analyses would only kind of be the subset of values when you really actually have elevated concentrations, rather than spending all this money and being out every 2 weeks to collect a bunch of non-detects in the off season. So it probably is going to, and I don't know if Rosie's still here. There's probably some complicated, I'm sort of assuming there's some complicated synthesis methods that could be used to go at a data set like this, rather than sort of feeling like we have to be out there every winter continuing to catch like bottles of water with no toxins in them. All right, thank you.
All right, thank you, everybody. Everyone, please make your way to your seat. We're about to get ready or get started. Our first presenter for Delta Smelt Session 3 is Veronica Violet with USGS. Her talk will not be recorded, so please take good quality notes. Thank you. Of the day is Matthew Young with USGS.
Last one. Good afternoon, folks. Can you hear me okay? Is the echo weird? No? Great, okay. Thank you, everybody, for sticking around to the end of the end of the end. I'm here to talk more about Delta Smelt, but I'm not going to talk about actual fish. I'm talking about what we can do when we know a lot about the fish, but we can't find the fish. This project was largely the brainchild of my co-first author here, Rosemary Hartman, and this has been like the best group project I've ever been a part of. Like, this has been a very productive, collaboratory team, and everybody listed on the slide has like done a ton of work leading to this talk that I happen to be giving to you right now. It's the end of the day, right? It's been a long time. I don't need to tell you guys some of this stuff, but I'm going to anyway, because we all kind of need a break. So I'm gonna tell you a story. A long time ago, there was a delta. And it looked kind of like that. It's changed a lot, obviously. A long time ago, a not so long time ago, there was a fish in the delta. You'll notice the tenses that I'm using. I'm being tongue-in-cheek, somewhat deliberately. Delta Smelt, this is a lovely painting by Rene Reyes. Populations have changed dramatically, and this has really influenced the types of research, monitoring, and tools we have available to understand Delta Smelt management in the system. Whereas before we can make decisions about this, now we are making decisions about this, right? So as water management and other types of management in the system take place, we're doing these often in the absence of the empirical data and empirical observations that we would really, really like to have. It's just a fundamental challenge with rare and endangered species writ large, and is something we're facing in this system right now. Luckily, we know tons about Delta Smelt. We know a lot about various aspects of their physiology, biology, ecology, all the ologies, especially with respect to what drives quality Delta Smelt habitat. In particular, some of these things tied to food, right? A fundamental constraint of any organism's habitat. Temperature, where do ectotherms like to live, right? Cold-blooded critters are especially limited by temperature. And turbidity, which is one of these things that is, I'm not gonna say unique to Delta Smelt, but one of Delta Smelt's quirks, right? This sort of like turbidity relationship that is not as fundamental to life. You know what I mean? Maybe you don't know what I mean. If you don't know what I mean, we can talk about it later. So there's been some excellent work by Will Smith and Matt Nobriga building on previous bioenergetics models. They published this update to Kenny Rose's bioenergetics model, where you take inputs about food, temperature, turbidity, and assumptions about physiological constraints and how those different inputs drive the relationships between inputs and growth, and understand the growth environment of a fish. How well can a fish grow with the fundamental constraints of these three habitat parameters? This is just a figure cadged directly from their paper with some paraphrasing, right? But able to sort of qualify the relative habitat across different regions of the delta, relative habitat quality across different regions of the delta over summer and fall, right? So purple is like good, high quality habitat. Yellowish is probably bad habitat, we think. And black just means it's too salty. We're not gonna find Delta Smelt there because it's sort of on the saltier end of their affinities. They did this across multiple years, across multiple regions of the Delta. It's a very helpful way to describe what might drive habitat suitability for this fish for this season. And it's awesome. We, the group of people who are listed on that first slide, saw that figure and were like, huh, that's weird. What's going on in region 6? Region 6 encompasses, in that manuscript encompasses sort of all of the North Delta, the Cache Slough complex, the Sacramento Deepwater Ship Channel. And in the paper, it looks really bad. But we see a lot of Delta smelt in the ship channel. So this here is just a figure showing the proportion of all Delta smelt caught in the summer of a given year, the proportion of that came from the ship channel. In most years, or in many years, it's over 50%. In some years, it's 75%. But if that bioenergetics model is saying the ship channel area is this bad, but we see this many fish there, what's going on? What are we missing? And what are the implications of this mismatch? There has been a tremendous amount of work. For as weird a place as the ship channel is, there's been a lot of work that's gone on there. Someone's calling me. That's really rude. I've never had, like, this is my first smartwatch, and so it just like threw me for a loop, so I apologize. But long story short, the ship channel is extremely complex hydrodynamically. There's a lot going on there that may provide some insight into why smelt are there, but why it might look bad in a habitat model, a bioenergetic model. This is a paper, or this is a figure catched directly from a different analysis by Fred Fira and others, just showing really strong spatial patterns in various constituents in the ship channel. And those constituents are the things that matter to smelt, in particular, turbidity, temperature, and food, right? Ton of variability here. And if you go ahead and look at where those smelt in the ship channel have been caught, you can also see that there's a ton of variability in the ship channel. It's not just that they are in the ship channel, they're at certain places within the ship channel. This is gonna come as no surprise to many of you familiar with the ins and outs of EDSM or the monitoring surveys, but the spatial patterns are profound. And this is what we wanted to deal with. All right, so we have this mismatch, bioenergetic model, empirical observations of Delta smelt in the wild. What do we do about it? We had two hypotheses. They're not mutually exclusive, but we addressed, well, actually we had a third one. I'm not we can talk about later. But one of these is that there's complexity in the ship channel, hydrodynamic complexity that provides habitat for Delta smelt that just gets washed out when you look at regional analyses, right? We call this the physics to fish hypothesis. There's a physical process that provides habitat nuance that results in a different outcome. The second hypothesis, it's a trap hypothesis, is that elevated catch of smelt in the ship channel is a mirage. They're there, they're not there by choice. They happen to get transported there through hydrodynamic processes or something else. And actually the ship channel is suboptimal habitat, and that's where Delta smelt go to die. I know I'm being silly because it's the end of the day and I'm trying to keep you awake. But we have these two hypotheses, right? A habitat nuance physics to fish hypothesis, or this sort of ecological trap hypothesis, and an ecological trap hypothesis. We revisited the same model that Will Smith and Matt Nabriga used for their analysis, and we just plugged in different data. There is, in all of those studies that I referenced earlier, there's this tremendous data set that's the compilation of an incredible amount of work from a lot of people who I will thank at the very end on zooplankton concentrations, on temperature trends over time, both longitudinally at different stations within the ship channel. You'll notice we had stations spaced across from the bottom to the top, showing different patterns in temperature. The blue here represents the bottom, right? It's a little bit colder there. And as you keep going upstream, it gets warmer and warmer and warmer, right? This is all for the same time period, but clear spatial patterns in temperature. The dashed lines there represent various physiological thresholds for Delta smelt, which regularly get exceeded throughout the summer and differently in different sites. We also have similar high resolution information on turbidity, which is this sort of master abiotic element for smelt. Again, variation in space and time, except instead of it being a clear gradient from top to bottom, blue and red, the topmost being red, bottommost being blue, both had very low turbidities. Whereas in the middle of the ship channel, there's this turbidity maximum, right? There's this very clear zone where turbidity is much higher than downstream and upstream places. Lots of reasons there. We plugged all of this data into a model. In particular, we had the best, most high quality, consistent empirical data from the year 2023. There are reasons for that I won't go into, but that's what we did. 2023, summer of 23, plugged all that data into a model, and we wanted to see how a hypothetical fish would grow, right? We'll be presenting everything relative to sort of an idealized growth curve. This expected ideal growth is like a von Bertalanffy, is from a von Bertalanffy function based on empirical estimates of length growth or age size relationships. This is what we might expect under relatively ideal conditions. And we'll be looking at sort of growth over time. So here on the Y, you have weight of the fish, and X is time since June 1st. And you can see at this downstream location, some deviation from expected ideal growth. This isn't unreasonable, it's there. Solid line represents bottom surface temperature. The dashed line represents bottom water temperature. Surface water temperature is the dashed line. We were trying to explore the possibility of stratification playing a role. It is minor, as you can see. As you go upstream, so we're moving to sort of the next upstream station, we saw growth curves that much more closely approximated what you might expect under ideal conditions. We were like, yeah, that's cool, right? That's awesome. And as you go up, it gets worse. It's real bad. Turns out the turning basin of the deep water ship channel might be the single worst place in the delta for delta smelt. And I do not say that lightly. It's very bad. But yes, there is evidence to support this physics to fish hypothesis. In 2023, at least, the hydrodynamics that drive tides structured habitat quality for delta smelt. Cool, great, awesome. What now, right? So we wanted to explore this ecological trap hypothesis. There's a reason why a lot of people don't necessarily propose ecological trap hypotheses, because they can be thorny to actually test. But what we wanted to do is instead dance around it a little bit and say, okay, it looks okay in 2023. Has this actually been consistent high quality habitat all along? Would that explain these catch relationships we saw prior to near disappearance from monitoring surveys? Or is this just a contemporary thing that we see that is irrelevant to previous observations? So we went in and put in a variety of other data sources. We actually went through and modeled water temperature data for the entirety of the ship channel for 30 years. That was its own beast. But long story short, instead of looking just at the summer of 2023, we are now looking at the summers of 1998 to 2023. Right, so now we have a whole time series that we can look at, and you can see this is just sort of what those temperature curves look like over time. The dark lines represent the sort of average water temperature across the 25-year data set, and each individual line's back there really fine. Doesn't really matter, but just so you know it's there. Trying to build trust. We'll look at this again, same sort of thing, right? We're really tied, all of our model outputs, we're trying to tie it back to something empirical. This is expected ideal growth based on well-established age size relationships. The x-axis, I'm shifting up the x-axis here a little bit. Now it's just gonna be a ratio. So greater than 1 means growing better than you might expect. Less than 1 is less well. And then ranging all the way down to 0, which you will see, or you'll kind of see. So here we're going to start at our bottom again. Right here we have our dark line represents the sort of mean expected growth, the ratio of mean expected growth at the most downstream location. And it's not terrible. It's not great, but it's not terrible. As you keep going upstream, you guys can't see. So there's the, oh, that's good. There's blue, there's this light blue, dark blue, purple, which looks pretty great all the time. You'll notice there's considerable interannual variation. Some years was really, really good. Some years were less good, but probably still within the realm of qualifying as at least moderate quality habitat. And as you keep going up, of course, it drops off. We're getting back to the turning basin, which is very, very bad. Very, very bad. What this means, though, is that there's a lot of evidence. The weight of evidence here suggests that parts of the deep water ship channel have been consistently high quality habitat for delta smelt for decades. That's also cool, right? That explains a lot of what we saw in variation of like actual observations of fish. Now I want to bring it back delta wide, right? So this is a similar plot to what Will and Matt published in their paper, just showing like a heat map in space and time. How do these things look for those same years? I pulled out the exact outputs that they had for the ship channel, and you can see there's some considerable disagreement, right? If you look at broad regional perspective, sometimes it looks good, sometimes it looks bad, but within the ship channel, where good and bad is a relative term. You don't need to get super caught up in it. We're gonna zoom even further back out. There's a point I wanna make with this. I'm going somewhere, I promise. We'll look at 1 year, right? In 1 year, if you look at the plot on your right, you see a lot of variation across the delta in a range of habitat. There's parts of it that are good, there's parts of it are bad. The point I wanna make is that just within the ship channel, you see just as wide a range of habitat quality. This one slough, this one channel, provides just as wide a range of habitat quality as delta writ large, which is kind of wild to think about and an important component of nuance. A lot of the ways we approach modeling, management, and many things in the system are by necessity set up to be regional analyses. There are lots of really good reasons for that, and I'm not gonna stand here saying we have to have nuance with everything, but I'm saying that the nuance matters, because this is how we a lot of people, myself included, can think about the system. But actually, the system works more like this, right? It's much more complicated. There's a lot of hydrodynamic variability, there's a lot of spatial heterogeneity, and this leads to a ton of nuance that we can continue to consider, we continue to build in our understanding of what's driving both, not just delta smelt, but other aspects of the delta's ecology. Here we had, I showed you that one channel can have as wide a range of habitat quality as the delta writ large. This just indicates that we have to keep considering scale in all of our management decisions. For example, you can think about supplementation decisions, right? It's not enough to say you want to release fish in the ship channel. Where in the ship channel you release fish would also make a huge difference. And this also highlights the importance of understanding mechanisms. This sort of analysis is only possible because there's a wide body of literature supporting the mechanistic underpinnings that go into the actual model. There were a lot of contributions that went into this on the back end, right? There's the author team, but the author team incorporated data from a lot of places. And so I wanted to be very clear how much we appreciate the contributions of all of the agencies collecting data on fish, zooplankton, temperature, turbidity. This type of synthesis work is, I think personally, is really valuable, but it's not possible without gobs and gobs and gobs and gobs and gobs of like freely accessible and consistent high quality data. So thank you, IEP community. It is truly appreciated. I would love to talk more about it. This paper has been submitted. It's in review in endangered species research. We got comments back, working through those. So it's coming soon to a screen near you. Yeah.
Thanks, Matt.
We're good. No questions. Sorry, we don't have time. I'm gonna wrap stuff up. I have a lot of people to thank, Stephanie and Christine, most of all for putting this on, being really the backbone of this whole process. Our planning committee, our session chairs, our volunteers, and most of all, you presenters, you really make this workshop what it is, and you have very high standards, and we appreciate that. As a reminder, please, well, let's all give ourselves a hand for that. Good job, everybody. Thank you so much for all you do. Reminder, drop off your badge holders. They can be reused. The feedback survey is up on the IEP website. So please, while everything is still fresh in your mind, go ahead and fill out that feedback survey. I am looking for a co-chair / understudy for next year's workshop organizing. So please keep that in mind. And our early career scientist awards will be indicated on the website and will be contacted in person. Just because we didn't have time to calculate everything and do the award ceremony right now. With that, thank you everybody for another successful workshop, and we'll see you next year.